Welcome to the first session of the morning, of the day. The first speaker today is Franz Pretorius, and he's going to tell us about testing general relativity with black hole mergers.
Okay, thank you very much, and thank the organizers for inviting me here. This has been a very interesting conference so far. Right, so I'm going to talk about testing general relativity with binary black hole mergers. In particular, the regime that I'm interested in is the dynamical strong field regime of relativity. So I'll very briefly explain what I mean by that. Then I'll also very briefly say what LIGO has already told us about the dynamical strong field regime. And of course, with the historic detection 3 years ago by LIGO, we finally started being able to get direct tests of the regime of relevance to black holes and horizons. But one of the main sort of motivations or takeaway points from this talk is that if we want to say that we have actually consistent general relativity, one of the problems is that we don't really understand binary black hole mergers in any theory other than relativity. And so our ability to constrain or rule out our alternatives is very much limited by a lack of knowledge of gravity in this regime other than general relativity. So perhaps the main motivation for this talk or for some of the work that I'll present later is this question: are there any viable modified GR theories that predict interesting differences for the coalescence phase of binary black hole mergers? And by viable here I mean a theory that possesses a classically well-posed initial value problem for which we can make concrete predictions of what the merger waveform should look like. And by interesting I mean if we take that modified theory and we subject it to the battery of tests that general relativity has already passed in the solar system, binary pulsar, etc., that theory has to be consistent with those tests, yet predict observable differences for binary black hole mergers. And I just want to say that the reason why I've the reason why I've sort of highlighted and emphasized these words is because I'm very particular about what I mean by viable and interesting. I don't want to say that some of these theories or suggestions aren't interesting or viable in other applications, for instance, cosmology or quantum gravity. I'm very much focused on sort of this astrophysical-sized black holes, classical gravity, and applying it to the merger regime of binary black hole mergers. And then sort of the second half of the talk, I want to present some results. This is largely done by a student of mine, Justin Ripley, on looking at one candidate modified gravity theory called Einstein-Dilaton-Gauss-Bonnet gravity. And so there have been a lot of studies of this theory before. What we've done is because we're interested in the dynamical strong field, we decided to try to approach this theory by solving the equations in a dynamical strong field setting. But to make the problem tractable, we started with spherical symmetry. So we're going to look at gravitational collapse in spherical symmetry in EDGB gravity and try to address this issue of viability. And I'd say that there's sort of mixed results. One is that if we fudge a little bit with realms of validity, we can say that this might still be viable. But perhaps the main takeaway point is that there are regimes where this theory ceases to have a well-posed initial value problem. Essentially, the equations that you get turn out to be what are called mixed type, mixed elliptic hyperbolic type. And I'll explain a little bit why that is so disastrous for it being a viable theory. Okay, so what do I mean by the strong field regime of gravity? So that's a regime in general relativity. So it's a metric theory of gravity. Gravity is curvature. So the strong field regime happens in relativity when some length scale in the problem is comparable to a curvature scale in the problem. So general relativity has no intrinsic length scale in it, and so it's some other property of the system that sets the length scale with which you want to compare a curvature scale to. And so for compact objects like neutron stars and black holes, it's the mass of the object that sets the scale. So getting to the strong field regime of relativity, if you say, let's pick a mass, well, then we get to neutron stars and black holes, then we get to the strong field regime in relativity. And incidentally, interestingly, if you look at the universe as a whole, not just at the Big Bang, but any time in the evolution of an FRW universe, on scales of the Hubble radius, by this definition, we are in the strong field regime of relativity. So, of course, what's interesting about general relativity as opposed to Newtonian gravity, for instance, that strong field doesn't just mean strong gravitational forces. In general relativity, when you approach the strong field regime, the structure of space-time qualitatively changes. And the most extreme manifestation of that is when gravitational collapse happens and we form a horizon. So the consequences of that, of course, in classical relativity are quite profound. When gravitational collapse happens, the singularity theorem saying that the theory necessarily evolves to a state where it breaks down and we need something like quantum gravity. That, of course, occurs inside black holes, and if cosmic censorship holds, then perhaps for astrophysical mergers we won't actually necessarily see what's going on inside gravitational collapse. But I think it's a pretty profound prediction of the theory that there can be regions of space-time that are undergoing gravitational collapse, and observations are saying that they're ubiquitous in the universe. There are black holes, in many, many flavors throughout the universe. So the dynamical regime that's also relevant to studying this using binary black hole mergers is when the luminosity approaches the Planck luminosity. Now, again, I'm just thinking about classical gravity here, but the Planck luminosity is interesting if you notice that there's no h-bar in it. So it's a classical number in some sense. But I mentioned general relativity doesn't have a scale, so where is this coming from? But it's interesting in the sense that if you try to imagine some causal process in relativity where there's emission of gravitational waves that's above the Planck luminosity, what you'll generically find, there's no proof of this, but you do little thought experiments, that either there'll be a naked singularity or there'll be so much mass in the region it will collapse to a black hole. So interestingly, it seems that this does seem to be somewhat of a limiting luminosity in general relativity, even if there's no scale in the theory. So the dynamical strong field regime is when emission can approach the Planck luminosity. So for astrophysical mergers, it doesn't get quite here. It's perhaps a couple of orders of magnitude below that, but it's quite high. And where horizons are present in the space-time. So black holes are relevant. Okay, so despite relativity being over 100 years old, this sort of remarkable regime of the theory has only been subject to direct tests since LIGO's historic detection of gravitational waves. So we're only just entering the era where we can actually question those predictions of Einstein's theory. So I would say binary black hole mergers are ideal. So neutron stars are also in this dynamical strong field regime, but then we have to worry about effects of neutron star matter, so equation of state effects. So black hole mergers are ideal in that they modulo some circumbinary material, which we expect to be pretty negligible for these events, that they really are sort of space-time events, strong field space-time events. This is a vast field. Emanuele spoke about it yesterday, Luis a bit, and there are going to be other talks about this. So I'm definitely not doing this justice, but let me just mention one set of tests that the LIGO-Virgo collaboration has subjected the O1 and O2 binary black hole events to is the so-called residuals test. And that's perhaps the strongest, most agnostic test in the sense that it doesn't presume any alternative theory, but what's done is, for example, with GW15014 here is you find the best fit general relativity template, you subtract it from the data, and you search for excess power in the residual. And all the current events have so far passed this residual test in the sense that the residual is consistent with noise. Okay, so that's quite a powerful test. But one thing which is perhaps not optimal about residual tests is if you think, well, how do you do a residual test? We hear that LIGO is so reliant on templates. Well, the residual test is essentially an unmodeled burst search. So people in LIGO can know better than that exactly what it is, but essentially searching for signed Gaussians. So you're looking for excess power in certain time frequency bins. And so to actually detect something that's a small deviation from GR, and essentially these merger waveforms just immediately tell you that order 1 GR is correct for binary black hole mergers. So if there is a difference, it's got to be subtle. But this residual test is not going to see something subtle. It's going to have to be a very large signal for it to see that. So if we want to actually do better than a residual test, we actually have to have a concrete prediction where we can essentially come up with some template for what we expect and search for that and sort of dig deeper into the data. And this actually, it's a signal-to-noise 24 event. It's quite a good piece of data. So you expect that we might already be able to start ruling out alternatives or saying something more about it than just the residual. But unfortunately, the problem is this, that for anything except GR, we just don't understand this merger regime in modified gravity theories. And you can see this is where most of the data, the signal is in this regime. And I like showing this plot because this actually was from Kip Thorne back in the 90s, motivating us to solve this problem for GR. So we didn't understand the merger regime in GR. Luckily now we do, so we can interpret these waveforms. But every modified gravity theory, many of them, the perturbative regime, the in-spiral regime, there's been corrections have been worked out. In many of them, black hole-like objects have been found and ring down have been studied, but the actual merger regime is unknown in these alternative theories. So that's the motivation, is to find modified gravity theories so we can actually dig deeper into the data and constrain them, or perhaps find some subtle differences from GR. So let me just start with sort of what one could critique that this line of sort of research is, well, we don't see any problems, so why, there's no reason to fix GR for astrophysical compact object mergers, so are we just inventing problems to solve? Okay, I said, you could say that I said this. This is a critique, and I'm not going to defend it, so let's just leave it at that. That is a critique, that this is perhaps not that interesting until there's a problem that needs to be fixed. On the other hand, just from a purely theoretical perspective, one thing that I find sort of fascinating is how special and unique general relativity seems to be. But is that just sort of a consequence of us not really understanding gravity as a metric theory? What are the possibilities? And so if we want to say that the events LIGO scenes are consistent with general relativity, if we don't know any alternatives, what does that statement even mean? How strong is that statement? And perhaps one way to think about the motivation for this line of work is sort of the analogous question that you might ask for the propagating degrees of freedom of a metric theory. And you might ask, well, general relativity has two polarizations, plus or minus. Well, what could a general theory in principle have? And there we know the answer. There are 6 polarizations that are possible, and with certain caveats on what the generic metric theory might be. So general relativity is definitely not the only possibility. There's a vast family of other possibilities. And so we want to ask the same questions for a metric theory of gravity that has a strong field, where there are horizon-like compact objects. What are the possibilities? Is it only the curved 2-parameter family and the dynamics given by general relativity, or is something else? And right now, we just have absolutely no idea. So that's sort of what I'm sort of interested in getting at here. Okay, so there's a vast range, even though I said there's no theory where this has been worked out, there's a vast array of theories that people have suggested over the years, and the one that I'm going to be particularly focusing on the rest of the talk is the so-called Einstein dilaton Gauss-Bonnet gravity. So here, this is the Lagrangian, the R is the Ricci scalar, that's the Einstein-Hilbert action. And so this is a common way of trying to come up with alternative theories by adding corrections to the action. And as Luis mentioned yesterday, there are many ways of trying to add various curvature scalars, etc. This Einstein dilaton Gauss-Bonnet gravity, the way it does it is by adding the Gauss-Bonnet scalar, that's this quantity over here, to the action. But if you just added that with a coupling constant in 4 dimensions, you could integrate it out. It's a topological term. And so to make this dynamically interesting in 4 dimensions, you actually have to couple it to a dynamical degree of freedom, and that's this dilaton field. And that's just its kinetic term. And the various flavors of Einstein dilaton Gauss-Bonnet gravity depending on what the coupling looks like, potential terms, etc. But this is one simple version that we're looking at. So in the way of the interesting and viable terminology that I used before, what's interesting about this theory, if you think for possibly for testing general, or looking at this theory for black hole mergers, is that so this coupling parameter lambda sets a scale in the theory, and it turns out that black holes actually don't exist for scales smaller than that. But that's an interesting thing. But what's interesting for deviations from relativity, so above the scale, black holes do exist, but they acquire hair, the dilaton hair. So they can have significantly different structure from relativity, especially close to the scale. And why they're also interesting in the other sense, or sort of viable in one sense, that they say that, well, wouldn't this hair produce sort of dipole radiation, and binary pulsars would rule it out? Well, the interesting thing is with neutron stars, the way that the scalar hair or reaction to this Gauss-Bonnet scalar comes up with neutron stars is very, very weak. And it actually produces a field which decays like 1 over r to the 4th from the neutron star. So it's got very little effect on neutron star structure and does not, and because of that decay, it will evade binary pulsar bounds. So it's interesting. So this theory has sort of been called that there can be miracle hair growth. I think Ted Jacobson and a few other people have sort of used that phrase in the past. And essentially, so if you take a neutron star it doesn't have much of the scalar hair, but if you collapse it to form a black hole, then it would grow this significant amount of scalar hair. So it's interesting compared to other scalar tensor theories. Neutron stars aren't that interesting, but black holes are. The question, one of the main questions, okay, I think it is interesting for binary black holes in that way that I mentioned, but is it viable? And so it's on the optimistic side, like despite the fact that there are higher curvature scalars in the action, it's still only you get second-order equations of motion. So what Luis mentioned yesterday, the so-called Ostrogradski problem, is generically if you add higher-order terms, you're going to get higher than second derivatives, and they are generically ill-posed. But this is sort of the unique curvature scalar, the Gauss-Bonnet scalar, in addition to the Ricci scalar, which gives second-order equations of motion. So that's not sufficient for a well-posedness, but it's at least a check mark that this theory passes. And one other thing that our study sort of suggests that's optimistic about this is, well, even though it's second-order equations of motion, the equations are incredibly nasty and nonlinear. I'm not going to show any of them, but they're sort of similar to some of the things that we showed yesterday. And there have been examples in the literature or suggestions that even in spherical symmetry, the setting we're studying, you could get things like shocks or singularities that form. So it's still a well-posed system mathematically, but bad behavior could develop. But optimistically, we don't see that bad behavior in these cases. On the other hand, on the pessimistic side, I think Luis also mentioned this is one example of a so-called Hondesky theory, and it falls under the class that Popolo and Real showed for generic backgrounds is only weakly hyperbolic, or they weren't able to find a way of getting a strongly hyperbolic formulation of the theory. So that's a negative. And then I think, like in what we're showing here, and this has also been found in other Hondesky-like theories, is that in certain regimes, the equations of motion actually aren't hyperbolic; they're mixed type, and that's a serious problem. Okay, so I'm not going to go through the details. So this is just the spherical collapse. We're using Schwarzschild coordinates, so these aren't horizon penetrating. So we can't actually we can't sort of study the stability of hairy black holes, but we can study sort of approach to black hole formation and strong field dynamics. And so to sort of characterize the results, so there's these sort of two parameters. One is this eta parameter. So again, this is the coupling constant. So we don't have any other matter. So this dilaton field itself is going to be the source of gravity. So we take a little sort of a Gaussian blob of matter with amplitude phi, characteristic scale L, and dimensional analysis says that when this number is large, it's strongly coupled. So the corrections to GR become strong. So this eta parameter is going to define if it's a strong coupling case. And in general relativity, the strong field is the usual thing, the compaction, so the mass to radius. So if we approach 1, we expect black holes. So sort of cases that I'm not going to mention. So the weak field, weak coupling, everything seems to be fine, at least for the classes of initial data that we've looked at, the light crossing time of the simulation. So weak data, it just implodes through the origin and escapes back out to infinity. If we look at strong field data, but weak coupling, it also seems fine with a caveat that we can't evolve very long. So we start to form black holes, but then this is not a horizon penetrating slice. So the lapse freezes out, and so our slice stops. But it does seem that we are starting to approach the hairy black holes that people have found in literature. And the problem is when we go to the strong coupling regime. And here's sort of a busy slide, just for lack of time. I'll just mention, just sort of roughly explain, and essentially, irrespective essentially of the compaction. So strong field or weak field, if we make this coupling sufficiently strong, we can find regimes where this mixed type behavior sets in. And so this is sort of this plot is this coupling constant. This is sort of the amplitude of the field. And here this is roughly a measure of the ADM masses. And so essentially everything above here form these so-called elliptic regions. So let me just show you one example. So this was a case where we, again, starting with sort of a Gaussian-like pulse with some characteristic, with letting it collapse. And what I'm showing here are the metric characteristics of the light cone structure in this lower plot. So this is radius, and so this is zooming on the region that becomes problematic. This is sort of time. And you can see plus minus 45 degrees, that even though this is moderately strong field, so a compaction of 0.2, we don't expect it to form black holes. It doesn't in GR. But it's also sufficiently weak field that it doesn't change the characteristics. There's no tipping of the light cones. But what the top plot shows the characteristics of the dilaton equation. So the Gauss-Bonnet scalar. And so you can see, so initially things are fine, but then they start to, there's significant change in the characteristics. And actually what happens here is the characteristic speeds go zero, and then they become imaginary. And so this is a sort of a hallmark of one of these mixed type problems, where it's hyperbolic in a certain regime, elliptic in another one, and parabolic on sort of what's called a sonic line separating them. So one thing that I mentioned that's interesting about this, and this actually, initially we were very puzzled by this behavior, because I said that when things approach this, there's nothing unusual that happens in the fields. There's no shocks, there's no steep gradients that develop, so it's very surprising that things seem to go bad in that way. So, but there's none of that kind of pathology. So the pathology in the sense is that the initial value problem breaks down if it's a mixed type equation like this. But one thing you could say is, well, okay, and essentially then, we're trying to solve this as if it were a hyperbolic equation. Eventually the code crashes, and it's because we're trying to solve an elliptic equation like it's hyperbolic. That's stupid. You don't do that. So you can say, well, okay, we've identified this is a mixed type equation. Well, let's solve it as a mixed type equation. And so there's some hope that you might do that. And in fact, mixed type equations, they occur in many problems. Well, one common example is supersonic airflow over a wing. If you have a steady state, stable situation in certain regimes, it's elliptic. In certain regimes, it's hyperbolic, and you solve it as a mixed type equation. And there is in the literature sort of analysis of these mixed type equations. And essentially, so the two prototypical examples that are studied are the so-called Tricomi equation and the Keldysh equation. With the Tricomi, well, both of them, they're hyperbolic in this domain, y less than 0. They're elliptic in this domain, y above 0. With the Tricomi equation, the characteristics approach the sonic line orthogonally, and the characteristic speeds go to 0. With the Keldysh equation, they approach it tangentially, and the characteristic speeds diverge. And actually, the Keldysh equation has a lot worse regularity on the sonic line, as you can imagine by the way the characteristics are going. So the EDGB equations are very complicated, but by analogy, the way the characteristics are behaving, it seems like it's of this Tricomi type. And back in the late 60s, early 70s, Morawetz sort of proved existence and well-posedness for the Tricomi equation, so you'd think there's some hope. And one thing you can imagine how you might want to solve a problem like this. It's not easy, but you specify initial data, you solve it in the hyperbolic region, and then you come up with some inspired guess for some future surface, and then solve the elliptic equation. And then you can say, okay, well, we've got a problem. But it turns out to be worse than that. And so this is how Morawetz was able to show the well-posedness for the Tricomi equation. She's considered the Dirichlet problem on this domain. So in the hyperbolic region, there are two characteristics, A and B, and then this connected to the smooth curve C in the elliptic region. And it turns out that you only get a well-posed problem if you can specify initial data in the elliptic region, but only along one characteristic. You can't specify any data on this other characteristic. So what that's telling you is that this naive thought that I mentioned, well, just solve the hyperbolic equation until it breaks down and then come up with inspired guess. The fact that there's an elliptic region spoils the entire problem. You can't specify data in the past in the hyperbolic region. So this type equation just doesn't make sense as an initial value problem. And if you want to think, well, if we want a predictive theory, well, what do we mean by a predictive theory? I'm not sure what to make sense of something like this. So this is actually a pretty bad thing for EDGB gravity. And so I've got a couple of minutes left. So this is my last slide before the conclusions. Okay, so can we wave our hands and say, is there still a little bit of hope that EDGB gravity is viable for black hole mergers? Well, this plot that I showed you here, what it essentially says is, so pick the scale where the smallest black hole comes in. That's also the one where it's going to be the most interesting deviations from relativity. We want to apply this to LIGO, so let's pick that scale to be stellar mass, a few kilometers. The problem is that for weaker fields, in the GR sense, for weaker fields, on smaller scales, things become problematic much easier. So to avoid problems, you have to assume that there's no cosmological background to this field at all, that the only way that this dilaton field comes about is it's got to be sourced by other matter, through the Gauss-Bonnet scalar. Okay, so let's do that. So we say there can't be a cosmological background for this field. So this study we haven't done, but this is now just then from dimensional analysis. So now we say, well, so in these simulations, it was actually the Gauss-Bonnet scalar that was sourcing curvature, but now let's have other matter, say neutron star matter, source it. Dimensional analysis then says, so you pick that scale where you want black holes to start being. It says that then, if that's the case, if there's no cosmological background, you'll start getting problems if there's matter that's denser than the equivalent density of that smallest black hole. So for example, let's pick a black hole that's a solar mass. That's going to have a density a few times denser than neutron stars. So is there matter that's several times denser than neutron stars? Well, we don't think so, at least not in the present universe. The problem, though, is if you evolve backwards in time, at some point, the density of the universe does become larger than that. So if we sweep that under the rug, and I think you'd have to go to earlier than Big Bang nuclear synthesis. So if we sweep the problem back under there, you can say there's still a little bit of hope for EDGB gravity. But okay, so the conclusions, the exciting thing, of course, is not EDGB gravity, but it's LIGO. We sort of ushered in this regime where we can start probing the strong field regime and testing some of these most intriguing predictions of Einstein gravity. The agnostic tests will always be there, and if there is some deviation, eventually there's going to be a loud enough vent and we'll start to see a problem if there's a problem. On the other hand, I think it would be interesting to really explore like what could be, is relativity unique? Could there be differences? And of course, I haven't mentioned sort of exotic alternatives to black holes, sort of with other things. These things also seriously need well-posed theories to be able to make predictions to confront with the data. Yeah, thank you.
Questions for Franz? Avi.
So in numerical relativity calculations of black hole mergers, often you excise the region around the singularity. Yeah. I wanted to ask a more general question of how confident are we that that region that is excised is not having any influence or could have any influence under some unusual circumstances on the outcome?
Right, so something it's a self-consistency check. So we don't assume cosmic censorship. We can't. We don't know if cosmic censorship is satisfied. But if it doesn't, the codes will crash. So the thing is, so the way that excision works, or effectively these moving puncture methods, is if all the characteristics are leaving the domain, so there can't be any causal influence of that region, you're not allowed to put boundary conditions there. If you try to put boundary conditions, it would be unstable. But if at some point the characteristics start twisting around, not putting boundary conditions there would be unstable. So in some sense, we don't put cosmic censorship in by hand, but if it wasn't satisfied, we wouldn't be able to evolve the equation. So I think I'm fairly confident with all the cases that people have looked at so far, in four-dimensional, astrophysical mergers, even high-speed collisions, there's no sign of any violation. So what we do inside, whether it's punctures or excision, doesn't affect the exterior.
So, Franz, the class of Einstein scalar Gauss-Bonnet theories that you considered are the ones that are shift symmetric that Thomas took in his papers. Yeah. Those theories and the ones that were considered by Cauchy with a real dilaton do not have Schwarzschild black holes as a limiting solution. Right. And in the class of theories that we've been looking at more recently, if you have a coupling function where the first derivative of the coupling function goes to 0, then you can construct black holes, at least in the static limit, that have a Schwarzschild solution as the limit. So the question is, did you try coupling functions that are different from the linear one? And do you have any feeling for what would happen to the characteristics if you did?
Yeah, so short answer, no, we didn't. And that'd be a very interesting thing to look at. So my suspicion is that it's not the structure of the coupling function that's the cause of the problem. It's really all those other nonlinear terms. So my guess would be that it won't help with this issue of well-posedness in a certain regime.
So I have 2 questions. The first question is how, and this might be a naive question, but how is this different from normal Gauss-Bonnet correction? And the second question is, do you expect anything interesting to happen at ADS for EDGB
Sorry, say again. So
in the anti-de Sitter space for EDGB.
Anti-de Sitter space. Okay. So you mean by normal Gauss-Bonnet, you just mean with just a regular constant, right? So as I mentioned before, you have to go to higher dimensions for that to be relevant. So I think then it's called Lovelock gravity. And yeah, I know that Papalo and Rial have done studies of Lovelock gravity, and they say that it's not strongly hyperbolic. So it's got similar problems in higher dimensions where you don't need this dilaton coupling, where it's fine just to have the constant. In ADS, like I guess there the question is, I don't know, but I'm guessing on small scales, it's going to be the same. Where ADS might make a difference is if you make this coupling parameter of the same order as the ADS length scale, but I'm not sure how. In string theory, the leading order corrections in curvature are, you get one of these Gauss-Bonnet terms, but then you'd expect that coupling would be of order the Planck scale, for instance. So completely irrelevant for astrophysical black holes, but I guess in ADS, it could be very relevant on small scales or any scale, but I'm not sure. If you want to see something interesting, okay, forget about, say, string theory motivations, where the cosmological constant is relevant, I think you'd have to pick those scales to be commensurate. But I don't know if anyone has looked at that yet.
One more question.
What you're saying is that we won't be able to make these tests based on trying to solve the initial value problem.
Right.
But that happened in GR itself. Cauchy evolution breaks down sometimes, and we try to extend beyond the Cauchy horizon by laying down some principles of symmetry or something like, or analyticity or something like that. Do you think that at least in principle it's possible to do the same? To do the same in these cases, not solve an IVF, but try to extend past the sonic line, construct a full 4D model, and analytically or numerically in this way, construct predictions.
Yeah, I think in principle, yes. I think that in practice, what's difficult about this is we don't have any guidance for what might happen. So, for example, in the hydrodynamics case, we can actually look. You can construct these sonic flows about, if you know what should be happening, you can make sensible conditions to solve the problem. Or for example, with the inner horizon, that's like one thing you mentioned. There's a Cauchy horizon, general relativity. You can posit that there's a smooth analytic extension across that. That might not be physically relevant, but you can do things like that. The problem is with this EDGB gravity theory, there's no sort of observational experimental insight or we don't have any analyticity problems on this boundary. So I think yes, the answer is yes in principle, but I don't see, I haven't been able to figure out any principle that will suggest how you might be able to get past that.
All right, let's thank Franz again.
Thank you.
So our next speaker is James Weatherall, who's going to tell us about where general relativity breaks down.
Okay.
I'll put you up there. That's actually because I haven't switched.
Oh, I see. Okay. Great. Thanks, Paul, and thanks to the organizers for inviting me, and thanks to everyone for coming. I can just push the button. Yeah. Okay, so there are startling thematic similarities to the last talk. It's almost as if someone planned this. So I'm going to begin with some, take it back, I cannot, with some motivation from a philosophical perspective for what I'm going to talk about in the form of a Galilean dialogue that tracks certain themes that have been present and influential in the philosophy of science literature for the last half century or a little bit more. Okay, so begin with a claim. This is known as the pessimistic meta-induction, attributed here to the Pope. Simplicio, The history of science shows that past scientific theories have turned out to be false. Thus, today's theories are likely also false. To which it is responded by Salviati, to the contrary, at least in physics, past theories have turned out to be approximately true, as limiting cases of truer theories. To which Simplicio responds, perhaps, but if so, we can only know that after we have our next theory. In other words, current theories are false in ways that we cannot anticipate. Salviati replies, again, I must disagree. The lesson of late 20th century physics is that our current theories are merely effective, applicable at low energies. We already know that new physics is needed at high energies. Enter a third voice, Sagredo, the voice of the common man. That's great. My favorite theory, general relativity, is plagued by conceptual puzzles, such as singularities. Will those problems get resolved by new high-energy physics? Salviati replies, yes. We should expect general relativity to break down at high energies and be replaced by a quantum theory of gravity. He then elaborates, it will be simple and beautiful and problem-free, and it will bring world peace and reverse climate change. Okay, so I want to highlight two issues raised in this dialogue. So one issue is the question of, to what extent can we anticipate where our current theories will fail, and where we can say we already know they will be approximately or effectively correct. Now, the basic issue here I'm going to suggest is that we have two competing kinds of considerations in the context of general relativity that bear on this, and it's not clear that they're compatible with one another. The second issue is, to what extent can we take problems in general relativity to be high-energy problems that we can already anticipate will be resolved by some, say, UV-complete high-energy successor theory. And so the answer to the first question, just to anticipate a little, I'll elaborate at the end. Perhaps not quite as well as we think. The answer to the second is, it depends. Okay, so to get at these issues, I am going to address two specific questions. One, what is the high-energy regime in general relativity? And two, is it the case that general relativity should be seen to fail or expected to fail only at high energies in that sense? So first, this question. So what do we mean by high energy? And this is connected to Professor Pretorius's remark that there's no scale in general relativity. And so there's not a natural sense in which you can point to a single number that we associate with general relativity and say large or small relative to this is the relevant question. And so one instinct you might have, and I think that this is not wrong, but not exactly to the point, is that we should think of general relativity in the the high energy regime as being general relativity in the context where very energetic phenomena are occurring. And so certainly you would expect that if there are Planck scale processes occurring in some part of the universe, that general relativity is unlikely to be the right theory of gravity or the right theory of background space-time geometry to treat them. And so this version of the answer is to say we should associate the high energy regime in general relativity with large stress energy, i.e. the high energy regime in matter theories. But of course that can't be completely satisfactory because we'd also like to say that there are strong field situations in the purely gravitational sector. And so now you might say, well, set aside matter, we should also expect general relativity to break down in the presence of large gravitational energy. Now, that should start making you a little nervous, because of course, it's been known for a long time that we don't have an unambiguous, covariant, local characterization of gravitational energy. And now before you jump in and say, but we have ADM mass and that solved all the problems, well, I don't think that that's really getting at what the issue is here. Because what we really care about when we're talking about general relativity breaking down in a high energy regime is that we're imagining that there's a universe. And in most of that universe, it's going to be the case that general relativity works perfectly fine, but then in some localized regions, it's going to break down. And so we really need to be able to associate energy with regions locally in order to be able to say it's here that we should expect some other dynamical consideration, some higher energy theory to matter. And so we can't just point to gravitational energy or quasi-local or non-local notions of gravitational energy to deal with this. Okay, here's yet another suggestion, I think also very much compatible with the last talk. Let's suppose, perhaps, that large curvature is what indicates the high energy regime. Now again, we immediately have to deal with a classic problem, which is that curvature is a tensor, and so its components can become large or small for reasons that have nothing to do with pathologies of the geometry of space-time, but rather have to do with pathologies of our coordinate systems. But okay, we have a way of dealing with that. Let's look at curvature scalars and take them to indicate high energies. So I think that there are lots of virtues to this proposal, and it's sort of the rough and ready one that I'm going to work with, even though it's not perfect for reasons I'll explain. Here are the reasons why I think it's a good idea. Generally, of course, curvature measures tidal forces. Tidal forces are naturally thought of as the strong, large tidal forces are naturally thought of as the strong field regime. And so it's natural then, I think, to think of the strong field regime as the high energy regime, even if it's not totally clear that we can say, and here's the energy that's becoming large. Another consideration is that it's, of course, the Ricci scalar that appears in the Einstein-Hilbert action. If you imagine, from an effective field theory perspective, expanding the Einstein-Hilbert action by adding further terms, those terms would generally be other scalars constructed from the curvature and perhaps its derivatives, generally higher order in the Riemann tensor. And so you might then think it's when those terms become large relative to, say, some cutoff that we should expect the theory to break down from an EFT point of view. So even if we don't necessarily think of those as tracking gravitational energy, nonetheless, they're playing the relevant role in the action. And then finally, in other theories, it's curvature scalars that measure energy density. So in electromagnetism, the stress energy tensor is, for instance, has the term FAB. Okay, is that perfectly satisfactory? Well, no. There exist singular solutions, plane wave solutions, for instance, of Einstein's equation, in which curvature becomes large or diverges, but in which all curvature scalars vanish. And so in these cases, we have a sense in which the theory is singular, where you might want to say the theory is breaking down, and nonetheless, no curvature scalar can measure that because the curvature scalars are identically zero. Now, I'm going to skip this, but I can come back to it later. There's an electromagnetic analog if you want to think about what those sorts of solutions are like. Okay, so just to summarize where we've gotten, I think it's probably right to say that the large curvature or large tidal force regime is the right one to think of as the high energy regime. But even once we've said that, it's not really clear that we can identify some single scalar quantity whose large value always and unambiguously signals that we're in that regime. I take this to mean that we apparently can't simply set a scale and say relativistic phenomena above this scale, characterized by a particular scalar quantity being above this scale, is when general relativity should be thought of as breaking down. And so we can't say something like there's an electroweak symmetry breaking scale, and above that we shouldn't expect QED or the electroweak theory to work or something like that. Okay, so that's the first part. Now the second question is, once we've got a notion of what the high energy regime is, does general relativity fail only at high energies? Now, of course, the background for this is the observation that there's a large literature in quantum gravity talking about how quantum gravity is going to resolve singularities. That often involves putting some sorts of constraints. So somehow quantum gravity is supposed to put a lower bound on something like volume or area in the classical limit. And so we're going to not have singular behavior in the successor theory. And so now we might ask, does the sort of mechanisms that are going to resolve singularity is going to resolve all of the problems in general relativity. Okay, so let's first just say we're going to take singularities to be an example of the sort of thing that signals failures of general relativity. Now, this is a philosopher's example. Doesn't mean it's not a good example. It's not the kind of example I think physicists think about very much right now. But look, there exist spatimes that are flat, inextendable, and geodesically incomplete. Such spacetimes are singular in the sense of being geodesically incomplete, even though they have vanishing curvature and curvature scalars. So I just want to observe, I don't think that there's a chance that the sorts of mechanisms that are going to resolve singularities in sort of strong field dynamical regime are going to tell us anything at all about these sorts of cases. But I'm not that interested in thinking about these right now. So let's just stipulate that we don't care about them. What we care about are only curvature singularities, broadly construed. Those are the ones that we're going to take to be the physical singularities. And then I think it's more plausible to say that quantum gravity is somehow going to resolve them. But that doesn't completely solve our problem, because there's another class of phenomena in relativity that I, at least, take to be as problematic as singularities. And these are Cauchy horizons. Now, I suggest that these are just as troubling as singularities, and in fact, for similar sorts of reasons. Because, so recall, a Cauchy horizon is a boundary of the domain of validity of an initial value problem. Initial data can't be evolved in sort of the local evolution sense that we get with hyperbolic systems past a Cauchy horizon. Now, of course, in some cases, space-time can be extended, but it has a different character, right? So I think that we should think of Cauchy horizons as reflecting a failure of the laws of physics to determine or generate future states from past ones, at least in a local way. And of course, in cases where we do have extensions, we have failures of uniqueness. And there's a sense in which you have to sort of construct the extension globally, if you like, rather than simply letting the equations evolve step by step. Okay, so now of course, it's also the case that Cauchy horizons appear in spacetimes that are not, constructed through weird cut and paste procedures. They appear also in more realistic sorts of scenarios, like in black hole spacetimes. And like singularities, Cauchy horizons are logically unrelated to curvature. So one can find examples of flat and extendable spacetimes with Cauchy horizons. And so high curvature isn't relevant, or isn't necessarily relevant for Cauchy horizons. Now, even in cases where there is curvature, right, so you don't have the flat spacetimes with Cauchy horizons, even if you allow curvature, in realistic cases like Kerr, for instance, curvature and curvature scalars are generally bounded in the vicinity of the Cauchy horizon. We can extend past the Cauchy horizon in Kerr, which means that everything is well behaved at the Cauchy horizon, except for the breakdown of the initial value problem. And so I think this raises a question. If we want to say that a future high-energy theory is going to solve the problems of general relativity, will quantum gravity resolve physically relevant Cauchy horizons? Now, I contend that the answer to this depends on, in an interesting way, on the resolution of the strong cosmic censorship hypothesis, and that it also suggests a somewhat different perspective on the strong cosmic censorship hypothesis than one gets from the literature of mathematical physicists who are trying to solve it. So, something went wrong with my pauses. Let me just remind you, the strong cosmic censorship hypothesis says that generically, the maximal Cauchy evolution of suitable initial data is locally inextendable. The general motivation for this, as someone like Penrose would give it, or someone like Mihalis de Fermos would give it, is that the strong cosmic censorship hypothesis says that general relativity is generically deterministic in the sense of local Cauchy evolution, right? So one way of thinking about what's going on here is that it's telling us that we don't get these situations where I can continue past the Cauchy horizon but do so without having the kind of local evolution implicit in the standard existence and uniqueness theorems. Now, why should we think this is true? I think that Penrose had an important intuition that's played a role in many of the arguments concerning strong cosmic censorship subsequently, related to the blue shift instability. And so the basic idea was supposed to be that if you have a Cauchy horizon and you send signals towards it, you should expect those signals to become infinitely blue shifted as they approach the horizon, which in turn means that the energy associated with the signal should diverge, which in turn might make you think that curvature is going to diverge through Einstein's equation as you approach the Cauchy horizon. And so if you have perturbations to some initial data in a spacetime that has a Cauchy horizon, then you should expect singularities to form at or near the Cauchy horizon, preventing extension. Okay. So in other words, there's a sense in which the reason we should expect the strong cosmic censorship to be, hypothesis to be true has to do with a link between Cauchy horizons and singularities. Now, of course, there's been lots of recent work by De Fermos, Spirsky, Luke, and others bearing on this issue. And I want to point out, De Fermos and Luke famously show that for data in the interior region of a Kerr black hole, the maximal Cauchy evolution can be extended continuously, but not differentiably, across a Cauchy horizon. They claim that it will follow, assuming some other things turn out to be true, that the C0 inextendability formulation of Penrose's celebrated strong cosmic censorship conjecture is in fact false. In other words, that we should not expect there to be a generic singularity-related breakdown of Einstein's equation at the Cauchy horizon in Kerr spacetime. Now, I just want to emphasize that they're talking about the C0 formulation, which leads to the following question. Is continuous extendability what we should care about if we're adopting the perspective on strong cosmic censorship that I've just suggested? Now, the answer is no, I contend. And the reason the answer is no is that we could conceive of the strong cosmic censorship hypothesis as the conjecture that Cauchy horizons should be thought of as themselves being high-energy phenomena. In other words, we should think of Cauchy horizons as being generically associated with unbounded or undefinable curvature, i.e. it's the curvature, not the metric, that we should be looking at when we're thinking about the breakdown of general relativity in some region of spacetime. And so from this perspective, the C0 conjecture, the one where we ask whether or not we can continuously extend past the Cauchy horizon, is physically uninteresting, because we already know, insofar as you can't differentiably extend past the Cauchy horizon, that general relativity should be seen as breaking down. This is the regime where quantum gravity effects should matter. And so that you can extend doesn't mean that that's the right physical description of nature past the Cauchy horizon. And so from this perspective, the De Fermos and Luke result is important, but for different reasons than what they give. In particular, it provides evidence for what I would take to be the physically more relevant version of the strong cosmic censorship hypothesis, which is that quantum gravity, insofar as it resolves curvature singularities, can also be expected to generically resolve Cauchy horizons. Okay, and so just to return to the 2 points with which I began, the first question, can we anticipate where our current theories will fail and where they will be approximately or effectively correct? As I said, really what's at issue here for me is that there are 2 competing intuitions. One is we should think of general relativity breaking down where there are singularities in the sense of geodesic incompleteness, or I also would argue Cauchy horizons, and then also this argument that we should expect general relativity to break down in the high energy regime. And I want to say that probably thinking of it in terms of the high energy regime isn't going to be perfectly reliable. We can't really set a scale and say that if a fixed parameter approaches that scale, the theory breaks down. More generally, what we can do is show that the theory, we can recognize that the theory shows pathological behavior even when curvature vanishes or is small. And then can we take the problems in general relativity to be high energy problems? Well, That, I claim, depends on the resolution of the physical version of the strong cosmic censorship hypothesis. And also whether or not these sorts of other pathologies, low curvature pathologies, can be eliminated by other considerations that don't have to do with changing the dynamics by introducing quantum considerations, but perhaps have to do with changing the kinematics by recognizing that in some future theory, certain sorts of constructions for spacetimes turn out to be illegitimate or impossible for reasons that have nothing to do with energy scales. Okay, thanks.
Questions? Eric.
So, Jim, I'm curious whether you think that certain kinds of causal pathologies, like violation of chronology, is something else where that may signal a breakdown of GR and that we might expect quantum gravity would fix. I mean, and these can arise in very, intuitively speaking, low energy situations, Gödel spacetime, behind the Cauchy horizon and Kerr.
Yeah, so of course there's a close connection between Cauchy horizons and closed time-like curves, violations of chronology. And so they are also a failure of the initial value formulation. So yes. I mean, in some sense, I think sort of generically, if you don't allow holes of certain sorts, you should expect that Cauchy horizons should have closed time-like curves right past them. So you have violations of chronology when you have Cauchy horizons. Some violations of chronology aren't going to be associated with Cauchy horizons, but because they're pathological in even more severe ways, right? Gödel spacetime doesn't have an initial value formulation.
I'm sorry, I wasn't clear. Do you think that quantum gravity will resolve these as well?
Oh, yeah. I mean, so I think that the physically relevant violations of chronology are ones behind Cauchy horizons. So if Cauchy horizons are resolved, chronology is resolved.
So you approached the problem from general relativity, and there is another path, which is to start from quantum mechanics and ask what happens if you want to incorporate gravity into quantum mechanics. Would you like to elaborate on that?
Not really. I don't think I have anything to say. So the way that I'm thinking about it is you present me with a theory, and then under what circumstances can I, just reflecting on that theory, say, well, here's the part that's physically relevant, and here's the part that's not. And I'm suggesting that a particular heuristic that I think is widespread in physics is both more subtle to apply, but also perhaps more likely to be successful than we would have anticipated.
Yeah, but my point is you can ask also where quantum mechanics breaks down if you introduce gravity.
Yes.
And that's a different path. And maybe you meet in the middle somewhere. So have you thought about that?
I have not. If I knew where quantum, no, I don't know. I don't have a good answer to that question. It's an interesting one to consider, of course.
When do you consider it to be a change in the definition of singularity when we begin to talk about the Cauchy horizon as singular in the absence of an end of the trajectories of?
Yes, because Cauchy horizons are not generally associated with incompleteness of any sort.
Right. So and this other result of de Fermis and Luke, right, shows that you can continue past there. But how does is it worth calling it a singularity on physical grounds, or because does it tie to a mathematical notion of singularity as the singularity at the center does? In other words, what are these two notions of singularity? I mean, when we group them together and both call them by the same names, singularities, in what sense are they the same?
I see. Okay, so my claim is the way I want to understand de Fermis and Luke is that they're showing that spacetimes that otherwise would not be geodesically incomplete become geodesically incomplete when the initial data is perturbed. And so I'm not suggesting that Cauchy horizons should now be subsumed under a definition of singularity. I'm saying we have a definition of singularity, and we have Cauchy horizons. How are they related to one another? Well, it turns out that generically, one of them, if strong cosmic centrism is true, generically one of them implies the other, is the relationship that I would propose.
Okay, one final question right here.
Just wanted you to clarify what you claimed in your slide 20, I believe. How do the results by Da Fermos and Luke have any implication for the resolution of curvature singularities if they deal with C0? Why do you suggest that they might?
Because what they show is not just that it's C0 extendable, but that it's C1 inextendable. That in general, you're going to have basically they show that curvature can't even be defined in a distributional sense for perturbed initial data. And so what I take that to mean is if curvature did exist, it would certainly be infinite. And in fact, it's so badly infinite that you can't even define it distributionally. And so I take that to be a signal of the sort of strong field regime generically occurring at the Cauchy horizon. And so if you have some way of, for instance, if you have some lower bound on a volume operator, like people consider in loop quantum gravity, and you claim that that resolves curvature singularities, you should expect that to resolve this as well. That's going to be physically relevant in this regime if curvature can't be defined because it's blowing up so badly.
All right, let's thank James again. So our final speaker for today's session is Svetlana Georgestad, and she's going to tell us about kinematics of parsec-scale jets and gamma-ray blazars.
Hello, everyone. I would like to thank the organizing committee for inviting me to give this talk. Really, our Boston University Blazar group has been doing analysis of relativistic jets since the very long baseline array started to operate in 1990s. And these are my collaborators, which include our graduate and undergraduate students and also our colleagues around the world. We really have analysis of relativistic jet in blazars connected with the Fermi Large Area Telescope, which was launched in August 2008. There are many really reasons for this. For example, here you see the gamma ray sky, and blue it is AGN, and the third Fermi Lat catalog contains about more than 1,700 of identified gamma ray sources, out of which 2/3 are blazars. And so blazars is the most energetic, long-living sources in universe. And the class of blazar consists of two subclasses. It is flat spectrum radio quasars and BLAC objects. And here you see spectral energy distribution of one of the typical BLAC quasar, or a typical quasar 3C279. And the spectral energy distribution covers more than 15 decades in frequency. And besides that, these blazars show very fast variability. It is high variability in amplitude. They have on high energies, their luminosity goes up to 10 in 50 ergs per second. And they have very fast variability on time scale, hours, and even minutes. So there is also some kind of correlation between luminosity. Also, their spectral energy distribution show two humps. Two bumps. One, it is synchrotron bump, which is at low frequency, and emission here is assumed to be synchrotron emission. And another bump, it is an high energies called inverse Compton bump. But we are still really in understanding what kind of mechanism is responsible for this high energy emission. Whether it is inverse Compton or synchrotron self-Compton or external Compton or even hadronic model involve proton synchrotron emission. So, but there is also some kind of correlation between luminosity and position of these bumps. And for low luminosities, which is mostly BLAC object, these bumps are located at higher frequency because many BLAC objects are detected even at TV energies, while only a few, for example, these 3C279 are detected at TV energies. And their high energy bumps is located at TV energies, while for quasars it is in MAV region. Because generally M87 it is a celebrity now, I would like to compare the spectral energy distribution of M87 with that of blazars. And it is somewhat similar. We see these two humps, and really M87 is even has detection at TV, known to be a TV sources. But it is low luminosity sources similar to BLACs. Generally, it has a very low accretion rate compared with blazars. For M87, it's something about 10 in -5 Eddington rate, when for blazars it is about 0.1 or even 0.3 of Eddington rate. So it looks as M87 as a dying blazar. So we do, connected with Fermi Gamma Ray Telescope, we do observation with a very long baseline array at 43 gigahertz. It is really, oops, what has happened? No, okay, doesn't matter. So with a very long baseline array, which has a 10 telescope around the US, at 43 gigahertz, because it is the highest frequency on which you can do very intense monitoring. We do monthly monitoring. And we do also optical, polarimetric, photometric, and spectral observations with the Perkins and Discovery Channel Telescope of Lowell Observatory for a sample of gamma ray blazars. This is a sample which we observe. It includes quasars and BLAC objects. Mostly it is the highest, the brightest gamma ray sources in Fermi catalog. It is the brightest in general blazar at 43 gigahertz. It is also bright enough at optical wavelengths to do polarimetry and emission lines analysis. And also it has a fairly big range in redshifts. So what is our motivations? The main our motivation it is to connect gamma ray high energy emission, gamma ray ETV emission with processes which we observe in the jet. So, and to understand where is the blazar dissipation zone located with respect to black hole. Here you see some sketch of a blazar where there is a black hole, accretion disk, broad line region around and jet. And here you see the movie of M87 also. And the most prominent feature of a blazar jet and M87 including in this case, it is the core, which is the brightest and the flattest with respect to radio spectral index feature of the jet. So we really, according to our analysis of radio jet at different wavelengths, we consider that for blazars, radio jet or radio core is located fairly far from the black hole, something tens or even more parsecs from black hole. So that this part of the jet, which is close to the black hole, is opaque for us at current observations. And we know that the shorter wavelengths you observe, the closer to the black hole the core will be located. So that it is why it is very important to go to shorter wavelength as the EHT does. So, and at centimeter wavelengths and longer wavelengths, the radio core, it is most likely tau 1, optically, tau 1 opacity surface. While at millimeter wavelengths, we consider that it is possible, and there are some observational evidence for this, that millimeter core is a reclamation shock. In this case, it is possible that it is physical structure. So, in blazars, we think that the core is located something tens parsecs from the black hole. It is really different with respect to M87. It is found both on base of core shift at different wavelengths by Harder et al. That really the core, the radio core at 43 gigahertz of M87 is located very close to the black hole, something within 10, 20 gravitational radius. So here, our program really now include for each of our sources in the sample more than 100 epochs of observations, which we really imaging and model. We model it with Gaussian components. Here you see total intensity image of one of quasars. Here it is the total intensity plus polarized intensity by color of another quasars. So we model all images which we have using Gaussian components to determine some properties of each component, which include flux density, distance from the core, which is assumed to be stationary feature of the jet, and also position angle and size. And we identify these components along the epochs, trying to find their dynamic and also their dynamic and evolution. So I will show you some example of from our sample. This quasar 1222, which is very interesting because it is one of the brightest quasars which was detected at TV energy with time scale of variability about 10 minutes. So what is interesting here, all images have the same level of noise. So the lower brightness which we see, the same as all images. Here you see kind of developing of the jet. So by ejection of new components, which are ejected with different speeds. Difference in the speed is from 10 to more than 20, apparent speed, of course, 10 to more than 20 C, where the C is the speed of light. And you see different kind of position angle of these components in a jet. So in some sense, if we look at how this is projected angle of components on the plane of the sky, if we look on the relation between apparent speed in position angle and brightness in position angle, we see that really it indicates that we really see flux which is Doppler boosting, because the lowest speed have the brightest flux as it is expected. So another source, it is 0235, which is kind of half of Bielac object, half of Blazar, half of Quasar, which show unusual behavior which we never have been seen before. So here you see a component which goes to the northwest, and here the next, in several years, in 2 years, you see a component which goes to southeast, and then in several years ago, we see very nice jet which is developed to the west. So this kind of very big change of the position angle of the ejection has not been observed before in this source, and in general, in such a big difference in position angle almost covered the whole range of possible position angle, have not been observed before in relativistic jet. And also the speed changed dramatically from 2C to more than 20C. And the next source, it is 3C279, from which we really have it is the first source with superluminal motion detected in 1981, 1979, 1981. And we have a very long history about components injected, and the first component C1 was injected in 1981. And here we again see very different apparent speed in a jet, as well as different ejection projected angle. And also we see when the components have the lowest speed, they are the brightest. Really, using this large history of component injection for this source, which is here in this movie, you see previous components which is ejected really very along the jet direction. Max Planck group, using the data for 30 years, more than 32 components, proposed a supermassive binary black hole model, where there are two jets, two black holes, each with a jet, and two jet A, B, which have a different direction. They have also different black hole masses, ratio of black hole masses. For A is twice more massive than B. And within this model, each jet has a precession, and kind of precession in the observer frame is about 25 years. And they explain trajectory of all components from 1st to 31st. But I have one criticism. It is a very nice model in some sense, but I have one criticism for this model, that precession is about 20 years, and it is comparable with the period of time of observation about 30 years. So that it's really need to be verified on a longer time scale. Another thing that 3C279 was always a calibrator for M87 in the EHT observations. And here you see some early EHT observation in 2011 where there were only 3 stations. And it is really modeling image from these observations, using the data, which show very unusual direction of the jet. We have almost, at our survey, we have almost simultaneous observations with this EHT observation. And also our resolution don't allow to see very well the core here, but we see some extension of the core. And after that, we see some components coming to the south, which is unusual direction for this source. And later, in 2017 observations, AHT observations, we see, this is from paper 4 of the AHT collaborations. We see very interesting structure within this core at 7 millimeters. So all this structure is located within this core of 7 millimeter image. And we see some extension in the core region of 1 millimeter image, which is perpendicular to the normal jet. So that we really have a very strong bending inside of the jet. And it is possible we also see some recalibration shocks in the jet, which one of possible explanation of this. But maybe another interesting property of this jet is that we, if we look at the Planck spectrum of this quasar 3C279, we see that at frequencies which are higher than maximum frequency and which we see maximum in the spectrum doesn't become steeper as we expected from far infrared. In far infrared, it should be of this value, but it is much flatter in this case. So this assumes, or either we have another population electrons here with a much flatter distribution, or we have some kind of opaque but very compact opaque feature, but it is less beamed than the core. And or we have a significant contribution. There is some dust components in the jet. So that generally, if we look at each source in our sample, it is really puzzling, and it can be needs a lot of has a lot of interesting properties. So, but in general, if we look at our sample, that we to look at apparent speed which characterize the motion in the jet, we see that kind of more normal apparent speed is something about 8-10 C. It is for quasars. It is smaller for BLX, and for radio galaxies, it is also something within 5 C. But what is interesting also that we find a significant amount of stationary features in the jet, which is fairly close to the black hole. Here you see an image movie of one of the BLAC objects, which is BL Lacerta itself, which has really 3 stationary features in the quasi-stationary features in the inner jet, which in some sense are changing in brightness and somewhat in position angle, but they are stay at the same distance from the core. It is the core itself, then another feature and feature here. So it is really will be very interesting with the EHT observation, probe these stationary features in the jets and to see their properties. Also, some jet features do not show ballistic motion, and they show some kind of acceleration or deceleration. It is because apparent speed, it is kind of combination of the real speed in the flow and also viewing angle of the jet. That it is very difficult to separate whether this deceleration and acceleration is connected with the apparent speed or it is connected with the change of the angle. Really, in Lister and Marsh in 1997 did some kind of Monte Carlo simulation, and they showed that if we look at the acceleration along jet and perpendicular on jet, and acceleration of jet along the jet is higher than acceleration of perpendicular to the jet more than 0.6, the ratio, then it indicates that we see real acceleration or deceleration. So it is really change of the Lorentz factor. And from our analysis of the apparent speed in our sample, we found that quasars mostly continue to accelerate something up to several parsecs in the jet, while BLACs, they decelerate very quickly near in vicinity of the core. And so we use also our VLBI. I told you that from apparent speed, we cannot get exactly Lorentz factor and viewing angle of the jet. But we use our VLBI data to get as much information as possible. And one of the possibilities, it is to use slight curves of each component to get the Doppler factor using the time scale of fading of each component and its size. So this is angular size, and this is time scale of fading of components, assuming that decrease of flux is connected with radiative losses, but not with the adiabatic expansion of the jet at high frequency and fairly close to the core. So this allows us to get the Doppler factor for each component. And here you see distribution of Doppler factors which we got for quasars, BLAC, radio galaxies in our sample. And it is for quasars and BLACs, it is similar, and for radio galaxies, significantly less. And there is another way to determine Doppler factor. For example, on brightness temperature formalism, which was done by Talviki Harata et al., that they observe the brightness temperature, get brightness temperature from observation at 37, light curve of 37 gigahertz, and compare it with theoretical limit obtained by Reed Hat for equipartition conditions. So, and if we compare here I always BLAC is blue and quasars are red. Compare their Doppler factor with those which we got. They are in some reasonable correlations. And from here, no Doppler factor, no apparent speed, we can get a Lorentz factor directly, and we can get viewing angle directly. So from this, we see that in general, Lorentz factor maximum, at least for BLAC and quasar, is similar, and it is something about 10. But quasars has a very large kind of tail of very high Lorentz factors, when BLAC has opposites, fairly low Doppler factors for many sources. But there is a difference in viewing angle. So quasars show a much smaller viewing angle than BLACs. So this is generally within 1 degree, and for BLAC it is something about 2-3 degrees, but it is that which we expect for blazars to be very close to our line of sight. And the next point, it is when we see some projected opening angle, and we know viewing angle, we can generally estimate an intrinsic viewing angle of the jet. And here it is some intrinsic viewing angle of the jet for quasars and BLACs and radio galaxies, which is something within 1 degree mostly. For some, it is up to 3 degrees. And it is dependence between opening angle of the jet and Lorentz factor. And there, and as was in the model of Blanford and Koenigsegg, 1979, there should be a correlation, some correlations between opening angle of the jet and inverse correlation between opening angle of the jet and Lorentz factor. More Lorentz factor narrows the jet, and we really see this kind of behavior. What is interesting that Mojave survey, which does analysis of 15 gigahertz VLBI images by different way. They got an opening angle by different way, but they got a similar kind of dependence between the opening angle and Lorentz factor. So now I would like to show you some kind of multi-wavelengths light curves of our sources in our sample, which we collect with different telescopes. On the top, you see gamma rays light curves. Green, it is X-ray light curve, which is obtained with the Swift X-ray telescope, and yellow is optical, and you see also radio core and some for 230 gigahertz light curves from the SMA. So in some sense, there are very good correlations, for example, between light curves, for example, here for 0235, or here for the CTA 102, or here for, especially here for 21. So when we see very good correlation at different wavelengths. So this really make us think that generally we see a good connection between gamma ray outbursts and behavior of a jet. And here you see the correlation between Lorentz factor, which we got from our VLBI observation, and it is on parsec scale, with gamma ray luminosity. And also difference between peaks of gamma ray outburst and time of ejection components, which we see in the jet, but time of ejection when they were in the core. So that generally this make us think that many gamma ray flares has happened in the really in the core region of the millimeter jet. And here you see some cartoon which shows the black hole, accretion disk, and also molecular torus and jet, and also millimeter core. So it is possible that, of course, gamma rays come from the bird line region, especially at quiescent state, or from torus, but from our kind of analysis, we consider that gamma ray outbursts are connected with the propagation of superluminal components of the core, so the millimeter core. Thank you very much. I will finish because it seems to me over time.
We have time for one quick question. Ramesh.
Fantastic amount of information. I just one question about the time scale of variability in gamma rays. I think you mentioned a couple of times that it can be as short as minutes.
Yes, for example, for 1222 plus star16, which I showed, it was at TV at more than 100 GeV. Change of flux by factor of 2 during 10 minutes.
10 minutes. And you also mentioned 3C279, I think.
3C279 I show, and their time scale of variability about half of, my minimum time scale of variability about half of hour.
Half hour, okay.
Yes, there was a BLAC object, 2251,
yes,
which had 2 minutes.
Right.
Time scale of variability.
And many of these cases, it's as if these time scales are comparable to the light crossing time of the black hole.
It is no.
Okay.
It is, of course, it is one of arguments against our proposal that it is connected with propagation of the jet in the core, because consider that the jet, even with, I show that the opening angle is fairly small, it is that jet is fairly wide, so that it's not possible to have such fast variability and so far from the black hole. But we don't say that it is the whole jet should vary. It is maybe a very small part of jet can be really responsible for variability which we see. Especially we don't know, it is maybe connected with some magnetic connections which are happening during turbulence or something when superluminal components propagate along the jet. So, but it is one of the main arguments against that it can happen on the parsec scales, that high energy can happen on parsec scales.
All right, let's thank Svetlana and the rest of our speakers. So we will reconvene in here at 11 o'clock for the remaining sessions for the day, which will all focus on Event Horizon Telescope results.
The session now, it's 11. Is it 11? Yeah, it's 11. So welcome everybody to the EHT portion of our show. This is kind of the subject of our attention over the next few sessions. This is the image of M87, which I think just about everybody has seen. Raise your hand if you have not seen this image. Okay, perfect. And I think it's fair to say that it does open a window on some very, very new physics and new observations. And we're very glad that the BHI in particular has had a real focus and a real hand in bringing these images and this project to life. I want to start by grounding us a little bit. You'll see over the next couple of talks, or next few talks actually, some instrumentation, how we built the instrument, how we did the observations, how we made images, how we processed the data, how we modeled the data, and the implications for physics around a black hole. But I don't want to detract from the fact that this all is built on a very solid foundation of complete and utter failure. Okay, so in 2007, we made the observations that detected horizon-scale structure in Sagittarius A star, but it's a little-known fact that in 2006, we tried the same thing. And on the baseline between Arizona here, the SMT, and Hawaii, we put together a whole system here. You can tell that radio astronomers are very neat and tidy people. And the light bounces off this mirror here up into this dewar here. And we recorded data over a few days, and we came back and we searched for fringes for about 3 months and found absolutely nothing. No detection on this baseline. And it turns out it was because there was some fault in this receiver. And then we picked ourselves up off the floor, dusted ourselves off, and then did this experiment the next year, and we succeeded, and that's what people will be talking about later today. We also made sure to test all the polarization of light going through here. These are quarter wave plates. This is a wire grid over here. So a lot of attention to detail. This is all happening at 14,000 feet. People get very, very tired, and they take naps. This is one of our speakers, Jonathan Weintraub, who is shown here at 14,000 feet, taking a nap in the sub-millimeter array control room. This is how we roll, and we eat a lot of Trader Joe's candy. But I also want to talk about the collaboration, because when I first got started in this project, I thought, well, getting the shadow will be the best thing. But actually, I think the equal source of gratification is building and assembling this amazing team. And it's really, this has been a true team effort. So you see here at the second EHT imaging workshop, also held here at the BHI, a bunch of us here unveiling the first time we actually gained confidence in this image. So that's kind of a theme you'll hear a lot over the coming talks, that this is really a group effort. And we've grown, of course, so now we have 200 members, 60 institutes, 20 countries and regions. You truly need a global team to build a global telescope. And this has also caught the attention of the world in a way that I really didn't think it would, or else we couldn't have predicted it. And you can see here that this image on April 11th was on every front page of every major newspaper around the world. We estimate that 4.5 billion people have seen this image. I don't know what those other people are doing. And when we find them, we're going to show them the image. But it was quite something. And it's not always clear why this happens. But maybe a hint of this will come from kind of this assembly of images that Peter Gallison put together here, the history of science department here in the physics department at Harvard, and also a founding member of the BHI. And he calls our attention to the fact that early on, people were making images of the unseen, of the invisible. This is Hooke's first drawing of a flea. All of a sudden, the invisible world became visible to us. These are the first X-rays in 1892. All of a sudden, the interior of a living body became visible for the first time. Earthrise over the moon in 1969 gave us a new vantage point, made us feel vulnerable. And then maybe this will join those as the first image of what we think is the event horizon. And as you listen to the talks that come and that follow, kind of keep this in mind, that this is kind of a seismic event, but it's also made possible by people. And let's celebrate them. The last thing I would say is that the Event Horizon Telescope did get an award recently, a Diamond Achievement Award. The National Science Foundation bestowed it upon the full collaboration. I'm just going to read the citation. For harnessing the power of international collaboration to use very long baseline interferometry to produce the first direct visual imagery of the shadow of the supermassive black hole, the center of Messier 87, a galaxy in the Virgo cluster 55 million light years from Earth. I can't think of a better citation for a better group of people. Thanks.
Thanks, Shep. So our first speaker for this session is going to be Dr. Jeff Bauer. Jeff is the Chief Scientist for Hilo Operations in Hawaii and a Research Fellow at Asia A. He's also the Vice Chair of the EHT Science Council, and today he's going to be giving us an introduction to the EHT.
Okay, good morning. So my role here is to set the table for you. And throughout the rest of the morning and the afternoon, we're going to do a deep dive into all of the great details that led to this really impressive result. What I want to do is give you a sense of the history, how we got here, and the motivation for why we're doing this, and give you some sense of the challenges along the way. And just to emphasize Shep's point, of course, this is the image that the Event Horizon Telescope made of M87, and you know, I think the first thing to begin with here, right, is the exquisitely small scale of this, 42 microarc seconds in diameter, and providing this incredibly accurate measure of the mass of the black hole. As Shep said, this really was a global effort with the contributions of many, many people. This is from our last collaboration meeting just last November, where we were furiously planning out the papers that were published in April. Not actually writing the papers, but just planning them at that point. And just a few scenes from some of the many telescopes that contributed to this work: submillimeter array, Pico Veleta in Spain, the ALMA in Chile, the LMT, the South Pole telescope, the submillimeter telescope, and some of the many, many people that contributed to this. Really takes an enormous amount of effort to carry out these observations. 5 to 10 people per station, 8 stations, really an enormous amount of effort to just to carry out the observations to do this experiment. So here's the full author list on paper 1. So if you feel like you haven't gotten sufficient credit, there's your name on the screen. And a partial list of some of the many different people in various leadership roles in this project, many of whom are here in the audience and you'll hear from later. I think our story really begins here. Of course, not with this image, because this is a very modern image of the center of our galaxy, made with a Meerkat telescope a few years ago, but truly a spectacular radio image of the center of our galaxy on a very large scale. And buried down in this saturated region is Sagittarius A star, the supermassive black hole at the center of our galaxy. And its discovery 45 years ago, 45 years ago, 55 years ago, 45, was, sorry, I'm very jet lagged. Really, I think set us on the path towards making this image of M87. And this is the kind of primitive data. It was a 3-element interferometer image. It was made using an antenna that was deployed in order to validate the underlying theory of how the very large array would work. And so you see flat amplitudes as a function of time here, which were interpreted as the presence of a compact source in the center of the galaxy. And that compact source was what people were looking for as evidence for a supermassive black hole in the galactic center. And of course, we've had enormous progress in the decades since, in particular, near-infrared studies of the motions of individual stars has now given us incredible precision and accuracy in the mass of the galactic center black hole and the distance. And we now know those numbers to better than 1%, which is truly astonishing. Sagittarius A star, fortunately, is not alone in being a large angular-sized black hole on the sky. And while our interests and our motivations were initially piqued by Sagittarius A star, we quickly realized that the supermassive black hole in M87 was another potential target. And it has two important properties for that purpose. One is that it's of large scale on the sky, and the other is that it has a large millimeter wavelength flux, which makes it detectable. So why is it that it has this large angular size, and why is it that it comes out at about the same size as Sagittarius A star? It's one of those cosmic coincidences, sort of like the coincidences that allow us to have eclipses, that M87 is 1,000 times further away as Sagittarius A star, but it's about 1,000 times more massive. And as we've heard earlier, there's been some uncertainty about the mass of M87 from larger angular scale measurements, a factor of 2 uncertainty. And that led to significant uncertainty in what we would get from our measurements towards M87. Now, we've seen this image before, but it's been known for a long time that M87 hosts a powerful jet. It was first seen in the optical a century ago, although it wasn't understood what powered it or what it was at the time. At radio wavelengths, there's been a huge amount of work over the years showing the impact of that on scales as large as the entire galaxy cluster that it sits in, and then showing this self-similar jet as you go down to smaller and smaller scales and higher angular resolution. Most spectacular of the images of this jet from Craig Walker just last year, showing really incredible detail and structure in this. The other side of the motivation here, of course, comes from the theoretical side, and Bardeen laid out the idea that of the photon orbit, and that we would expect to see light focused into a ring at 10 gravitational radii, and then Luminet, a few years after that, published these hand drawings of his calculations. I find that to be a really astonishing thing, right? This is a kind of a pre-digital era contribution. Very motivating for our project was this paper from Falca, Melli, and Agol in 2000, which did simulations of the kind of image that you would get for Sagittarius A star. So taking into the known mass and distance at the time and just a simple isotropic cloud, and showing that, in fact, we expected to get a shadow and a ring-like feature that was present there. And subsequent theoretical work over the past 2 decades has continued to confirm that idea that no matter how what geometry, what microphysics you put into it, you largely get back something that looks like this, that looks like either a ring or a crescent. And that was quite motivating for carrying out this experiment. Okay, so some practical challenges here that drove us to the experiment and to Jono sleeping on the floor at 14,000 feet, right, is that this is really hard to do, right? So the expected scale is on the order of tens of microarcseconds. There's no way to make that kind of observation with any existing facility. There's no telescope that can do that. So to do it, we need a global millimeter VLBI array. At a wavelength of 1 millimeter, a baseline of around 11,000 kilometers, you get an angular resolution of about 20 microarcseconds. Just barely enough to make this work. So, of course, we had to invent our own network to make this work, and create an ad hoc network. Now, the next part of what's really difficult about this is that the atmosphere is very nasty at millimeter wavelengths. You have to be in very good sites around the world, and even there, the atmospheric phase fluctuates rapidly, which means that we only have a short time in which we can detect our sources. And then, while our millimeter telescopes are great, they're really not all that sensitive, and the number of sources that they can detect is actually quite small, in particular because of this very short atmospheric coherence time. And so the progression that we've gone through over the past couple of decades has really involved new telescopes with greater sensitivity and increases in bandwidth. And the introduction of ALMA to our array has really been transformative. ALMA is the largest millimeter telescope in the world, incredibly sensitive and in a great location. And as you'll hear about in significant detail from Jono, the advancement of digital recording technology that we've contributed to as a part of the project has been really central to increasing our sensitivity. So I think the modern story of millimeter VLBI really starts with this experiment. It was a 3-station experiment involving these stations. And this is Haystack Observatory, MIT Haystack Observatory. We didn't even get detections on Sagittarius A star to it. But we got this very limited amount of information that allowed us to set a limit on the size of Sagittarius A star. Over the years, many people, including myself, worked on measuring the size over a wide range of scales that got down to, at short wavelengths, around 10 Schwarzschild radii, but really only in terms of modeling a Gaussian. The EHT experiment took off, I think, with this measurement at 1 millimeter that we carried out using this, again, 3-element array, visibility amplitudes as a function of baseline length. When you fit a Gaussian to that, you get a size. You don't get an image. It's impossible to make an image out of that kind of data. And then we advanced on to M87 and did a very similar 3-station kind of experiment that allowed us to set a size. Again, a few Schwarzschild radii in scale, but really no ability to say anything else in any further detail about the source. So that brings us to the 2017 experiment, which ultimately led to our image. And you can see that we were working with a global array that's much larger in scale than what we had before, and actually produced a data set that was of high quality for imaging. Now, one of the things you're going to hear about in all the subsequent talks is all the different steps in making this image and analyzing this image and doing simulations of this image. And this rather boring slide is meant to make a really important point here. This is, to my knowledge, the most thoroughly vetted interferometric image ever made. That at every stage of our analysis, we had multiple methods that we compared against each other and cross-checked. We ran independent teams doing different steps. You're going to hear about all of these in a lot of detail in the upcoming talks. But we did this because we knew the measurement was so important that we didn't want to leave any stone unturned, any opportunity for someone to say, you know, oh, if you had processed it this way, you just would have gotten a disk, or you would have just gotten some fuzzy Gaussian. And so this sequence is really incredibly important for validating what we found. This is the view that, of the source that as I view myself as an old-time interferometrist from 3-station experiments. This is the view of the data that I really like. It's visibility amplitude as a function of baseline length. And you can see how much richer the data is than the earlier experiments. And overplotted on this dash curve is a Bessel function that it hasn't been fit to this data, but you know, you can draw it on there without any fitting. And when we saw this, we had a very clear idea that we were headed towards something very exciting. And so the Bessel function is the Fourier transform of an infinitely thin ring on the sky. And so the positions of these nulls, the height of this, all give us a very strong inference that we were in fact seeing what we expected to see. Now there are deviations from that, and this is by no means all of the data that we had. In particular, it doesn't incorporate the phase information, the interferometric phase information. But for those of you who don't trust the black box of I put data into a software package and an image came out, I think that this correspondence to the Bessel function is a very convincing demonstration of the reality of what we've measured. Okay, so there it is again. You'll hear later on about the detailed properties that we measure from it and the interpretation of those. It's in many ways a very simple result, really parameterized by only a handful of independent terms. The great thing about this is that it's not the end. It's really just the beginning. And so for the future, obviously, we're very interested in Sagittarius A star. We have terrific data. We're working on it. We have polarization data, which is going to tell us about magnetic field structures. We want to study the time domain for these sources, both on short time scales and long time scales. Future experiments will have higher image fidelity by adding in new stations, more bandwidth, so forth. And ultimately, I think there's a vision of finding more sources or looking at a greater ensemble of sources. So that's all I have. Thank you.
All right. Are there any questions for Jeff?
Thank you. So could you tell us on this image, but I'm sure we're going to hear a lot about it. So what's the percentage of that image that in terms of pixels, which is like the measure, the observed image, and the percentage which is inferred with these algorithmic methods, and
So I'm not sure I fully follow your question. I think one way to think about this image, right, is the diameter of the ring, which kind of goes from the center line to the center line, is this 40 microarc second scale, the kind of a largest scale around 100 microarc seconds on which we're capable of imaging, and then the beam size itself is about 20 microarc seconds. So there are a couple of tens of independent pixels in the image, but I think that's not exactly the question you're asking.
Well, yeah. So if I draw the lines that were observed, so if you have, is it like 1% of the number of pixels here is like the number of pixels of that image, is it like 1% observed and the rest inferred, or is it much more? Is it like 10% of it is really observed and the other one is inferred?
I don't think so. In some sense, the entire image is inferred, right? Because so the imaging process is a Fourier transform of the visibilities, right? So when we do a cross correlation between a pair of antennas, and we do that for all those pairs, and all those complex cross correlations that we measure form the two-dimensional Fourier transform of the image on the sky. And so the imaging problem that we face is to invert those measurements into the image domain, but to address two particular challenges. One is that we have to calibrate the data, that the data comes in and there are calibration factors that need to be applied. And the other is that it's incomplete, right? That we essentially have an incomplete mirror that follows where each of those pairs is on the sky. And so there's always some interpolation that occurs in an image of this sort between what's in the visibility domain and what lies here. But I think what you'll hear in a lot of detail in the imaging section talks is on how reliable those images are and all the methods we use to verify that. And then what you'll also hear is that we also did analysis only of the visibility data. So modeling only directly to what we directly measured, and not inferring anything else.
Any other questions for Jeff?
This is a very naive question, and I did see this picture many times, but can you remind me in this picture in particular, where's the jet that is coming towards us?
That's a great question. So the jet is off in this direction. We don't see any evidence of it in this data. We see if I go back to the visibility amplitudes. One of the things that we see right away, right? So this is the total flux of the source, and then this is our naive ring model, right? And you can see that we don't recover all of the flux of the source, and what that means is that we're resolving out the jet. So the jet features are too large scale for us to detect. So future experiments will enable us, we think, as we fill in the visibility coverage on this scale, will enable us to see the connection from this very small scale to the jet.
All right, let's thank Jeff again. Our next speaker is Dr. Jonathan Weintraub from here at SAO. Jonathan leads the design and deployment of the EHT's wideband digital instrumentation, and he manages operations at the submillimeter array station. Jonathan's been with the EHT since its earliest days, and today he'll be discussing the EHT from an instrument perspective.
Thank you. It's asking me about my keyboard. Just ignore it, okay. Oh, okay. Thanks. Okay, so thank you very much, Jeff, for setting the scene, and Shep for setting the scene. And Jeff, you set the scene so well, I didn't have time for my nap. I kind of had to pay attention. I'm the person who sleeps on the floor. My name is Jonathan Weintraub, and I actually, I'll first say that this is a very personal kind of story, and this particular photograph of the headlines across 3 major U.S. newspapers was actually taken up by my beautiful wife, Robbie Single, and I started working with Shep on early EHT observations back in 2006, when our firstborn son came into the world, and my daughter was born in 2008. And over the years, I've figured out I've spent well over a year away from home, sort of abandoning her with babies. And so she came and celebrated with us in DC and snapped this picture on the way to the airport, and I'm using it to introduce the talk in homage to her. I get to travel to beautiful places. I actually work for the submillimeter array. That's kind of my day job, and the EHT is a little bit of a sideline. So SMA on Mauna Kea is an 8-element interferometer, a little bit like the EHT, but itself, but on a smaller scale. And then our first experiments, the ones that Jeff talked about, setting the scene, were run with the JCMT, which is a 15-meter single aperture, and the CSO, now sadly retired, which is a 10-meter submillimeter antenna, pioneering submillimeter facilities on Mauna Kea. Because I was working out on Mauna Kea such a lot, by the way, this beautiful picture is taken by another EHT colleague, an SMA colleague, Nimish Patel. When Shep was looking for someone to work with on the early observations, he kind of found me. And Jeff already set the scene with these very early observations. Shep talked about a failed observation in 2006, and then we came back at it in 2007, attempting to get a first long baseline fringe on a 4.5-kilometer baseline from Hawaii to Arizona, and also Hawaii to California. And we ended up getting fringes from Hawaii, the JCMT in Hawaii, to the SMT, which is on Mount Graham, Arizona. Just these 4 rather low SNR scans out of about 20 scans on Sag-A-Star that we made, and no detections at all to California, even though we had detections from Arizona to California, indicating that both the Arizona and California Karma sites were working. Jeff talked about all of this, but my particular takeaway is this upper limit in California. We just weren't sensitive enough. We're barely sensitive enough to get the detections from Hawaii to Arizona. And this California detection might have told us whether the Gaussian fit was appropriate, or this bouncing visibility plot corresponding to a little bit of that Bessel function being the transform of a circular ring that Jeff talked about. And in 2009, we did more observations. Took us a while to publish them in 2012 on M87. So M87 has the same issue of is the data, the very sparse data, fit by this Gaussian, or could there possibly be a bounce in it? Because both the dotted line and the solid line equally fit the data, although you'd be hard-pressed to argue for the bounce. So here's the 2017 data, and again, this replicates what Jeff already showed, the beautiful Bessel function-like visibility plot. This is the length of the baseline, its visibility amplitude or visibility distance, and you can very clearly see that there are two beautiful nulls indicating that we're starting to see a ring-like structure in the source even before the imaging is done. And since my talk is about EHT instrumentation, that's my contribution, the purpose of showing this is to motivate for what made the difference between the barely identifiable Gaussian size measurement here and this beautifully elucidated, much more complex visibility structure. And the difference is instrumentation. The difference, I guess, in large part is instrumentation. From my perspective, it's instrumentation. The kind of software and imaging algorithms and the calibration also plays a role. But this is what we were working with at the time. This was a so-called digital back end. I'm going to give a little bit of a shout out to the Casper collaboration. I work for something called, I'm involved in a global collaboration of instrumentalists called the Collaboration for Astronomy Signal Processing and Electronics Research. And this IBOB is an early instrument, an early FPGA digital signal processing board. And this is a precursor to the Mark 6 recorders that we use now. It's called the Mark 5B. And we were recording at data rates of 4 gigabits per second. Now, 4 gigabits per second corresponds to 1 gigahertz in bandwidth. You translate, you record 2 bits of data, and you have to sample at twice the bandwidth. So if you want to sample a 1 gigahertz bandwidth, you have to sample at 2 gigasamples per second with 2 bits per sample, and that's where the 4 gigabits per second comes from. And what we needed to do was two things. One is increase bandwidth, and the other is increase collecting area. This is also early equipment. This is an early phased array system, also 4 gigabits per second. This is a very venerable antique atomic clock. You have to maintain coherence at the sites. We've replaced this now with a modern commercial version. This was built right at SAO by a guy called Bob Vesso, who passed away recently, but I had the pleasure of meeting. And it was based, actually, the physics of the atomic clock of the H mesers comes out of the work of Norman Ramsey in the physics department at Harvard. So we phased up the submillimeter array as one way to approach improving sensitivity. We have the JCMT's collecting area, a 15-meter single dish. The CSO is 10 meters at the time, now retired. But the SMA collectively, the 8 6-meter dishes, exceeds in aggregate the collecting area of either the CSO or the JCMT. And the fringes system shown in the previous slide is the first system that we built to phase up the submillimeter array. And it worked too. So this is actually a test where we broke out one of the SMA dishes, recorded it as if it were a VLBI single dish, and then stepped in, I beg your pardon, stepped in one dish into the phased array at a time. And the sensitivity of a VLBI baseline goes as the geometric mean of the collecting areas on the two sides of the baseline. So what you have is you're adding stepwise collecting area on one side of the baseline and making a fringe with a single dish antenna on the other side, and that gives you the square root of n characteristic as we add in dishes. So anyway, this was a, I like to think that we had lots of fun. When I wasn't sleeping on the floor, I was getting my frustrations out by throttling Shep. Michael Johnson came out and spent some time at SMA helping us with one observation back in the day. This is Andre Young, a very key guy, making observations. Rurik Primiani helped with phased arrays. A true unsung hero, a guy called Taco Young. And this guy, Dusan Pejakovic, is our program officer at the Gordon and Betty Moore Foundation, and a shout out to our funders. Dusan was messing around with our brand new H maser and a screwdriver just along the lines of having fun. So in addition to phasing up SMA, we also wanted to expand bandwidth. So moving from gigasample per second A to D converters, 2 channels of which gave us 1 gigahertz of bandwidth, we moved on to the next generation of Casper equipment. These are 5 gigasample per second A to D converters, new generations of field programmable gate arrays, the Xilinx Vertex 6 family. Field programmable gate array is a little bit like a computer, but it's rather more complicated to program, and it does very highly parallelized computation, so that you have, for example, 2016 multipliers distributed across this chip, and on every clock cycle you can do a multiply with each and every 18-bit by 18-bit multiplier, and that's what enables you to do very fast Fourier transforms, for example. Because all of this data that's sampled at 5 gigasamples per second in each of these A to D converters, and it starts off being 8-bit data, so you have a flood of 80 gigabits per second of data rate coming into this FPGA, and the FPGA has to process it in real time. And we have 8 10 gigabit per second Ethernet ports at the back, so that you can have the full throughput of data through this real-time processor. The A to D converter, 5 gigasamples per second is pretty darn fast. In fact, it's implemented with 4 1.25 gigasample per second A to D converters with clocks in quadrature phase from one to the other, interleaving the conversion rates, and the interleave isn't perfect, and you have to make adjustments on the FPGA on the A to D chip to take out these artifacts, lining up the cores in phase, amplitude, and gain. So Laura Vertetich helped take this Roach 2 FPGA platform, 5 minutes to talk, okay? And turned it into a back end that made recordings to Mark 6 data recorders, 2-bit data. This is validation plot. This dotted line shows a cross correlation at of 2-bit data, which is 88% efficient. So this is a dotted line with a slope of 0.88, with these lines lying on it, and the error bar is too hard to see. And 8-bit data is almost continuous, so you get a 45-degree correlation efficiency. And we continue to build things out from 4 gigabits per second to 16, which is 1 EHT backend, which was our first observation with this new technology, to 64 gigabits per second. And this is what it looked like. Laura, who did the FPGA design, and a variety of other people I've shown before. So we also built new phased arrays for the submillimeter array, something called Swarm, the SMA wideband astronomical Roach 2 machine, did phased arrays, processing at 64 gigabits per second. That's 8 times faster than what we had back in 2009. And it's a set of those FPGA processing boards arranged around a 10 gigabit Ethernet switch. You have to do full-blown cross-correlation. This became the facility instrument at the SMA, and does full cross-correlations for the SMA at 32 gigahertz of bandwidth with 140 kilohertz of spectral resolution. This resolution at the bottom here is just this little blue bit over here, which could be anywhere and yield the same resolution. Has a great deal of complexity between the cross-correlator and the phased array part over here. This is where the correlation happens. The correlation is done by doing a Fourier transform first. Cross-correlation is then reduced to a cross-multiply. And then even after recording the data, it can't be correlated directly because it's frequency domain phased array data, and it has that very high spectral resolution, and it's not actually sampled at the same sample rate for legacy reasons as other data. So Alex Raymond, who works in the instrument group sitting in the back of the room here, is currently working on a real-time version of something that we do non-real-time on a GPU processor, and this is called the adaptive phased array heterogeneous interpolating downsample for swarm, or APHIDS. It sort of goes with the Roach and other perverse acronyms that we come up with. And then the data has to be correlated, and this is just showing a CPU cluster where the correlation happens with Kazu and Jeff and Vincent colleagues. So phased SMA to phased ALMA fringe so we phased up SMA, a separate team phased up ALMA, the ALMA phasing project, and we got the first fringe in 2015, and as Jeff mentioned, that transforms the sensitivity, already transformed the EHT because it enabled this network calibration, because there's something very special about closure phase around a triangle that kind of knocks out the atmospheric effects. So it turns out that if you have ALMA fringe, from ALMA to a smaller station, most of the stations are small, all the stations are smaller than ALMA, and another fringe to a small station, that fringe tends to be very strong because you get the sensitivity of ALMA contributing as the geometric mean across the baseline, but you have the ability to do a closure phase triangle and over-constrain the phase on the small station to small station baseline. And if you divide the array up into triangles like that, you can do this very clever network calibration. Details in the second and third EHT paper. You take all these rather incoherent correlation functions and you can line them up in post-processing. We are moving forward now, designing currently with 16 gigasample per second A to D converters, putting 4 of them on a single board, going to 128 gigabits per second in a single piece of equipment. And we really want to put an EHT station in space. And the need there, that arises because it'll really help to fill the UV plane quicker, as this animation by Daniel Palumbo shows. So we have a low Earth orbit satellite orbiting the Earth and showing how with Earth rotation synthesis, you have rather slow filling of the UV plane, but you get a very crowded UV plane in the bottom panel. Daniel's sitting right in the corner over here. And we're really working quite actively to get an EHT station into space. This depends on having an anchor station on Earth, because the EHT station in space will be perforce small. So anyway, this then is my set of conclusions. Really, as again has been said before, this is just the beginning, right? We got this fuzzy image. We've got Sag-A-Star, which has the challenge of time variability. And we're building a system that's going to make sharper pictures, more time-resolved pictures, and really increase the science that the EHT can do. Thanks very much.
We have time for 1 or 2 quick questions for Jonathan.
Hi. What are the main technological hurdles that need to be overcome in making the space station? Are there new technologies that need to be developed, or is it just a matter of applying old techniques?
Yeah, so we are looking at this quite actively, and I would say that the challenges are, first of all, keeping it simple enough so that we can do it quickly enough with kind of a mission of opportunity. That means not flying a hydrogen maser time standard, but perhaps flying a simpler time reference like a crystal, or communicating the time reference over some link between Earth and the satellite. And the other difficulty is that the submillimeter receivers are cryogenic and run at 4 Kelvin. It's very, very hard to do cryogenics in space, particularly low Earth orbit, because you're very close to a warm Earth. So I would say that those are the areas of research that are potentially very interesting to pursue.
There is a lot of talk in Washington these days about getting to the moon by 2024 and establishing a settlement there. And of course, not much science is being discussed, but right. I was wondering, obviously there is no atmosphere there, so one advantage is to have an array there on its own, but then of course one can have also the Earth moon separation as an additional advantage.
Yeah.
Have you put thought to that?
You know, some time ago, I was on a research project looking at putting a low frequency array on the far side of the moon, and the idea there was to use the bulk of the moon to shield from Earth RFI. This is a little bit different. I should have mentioned one other technological challenge with satellite in space. The EHT generates enormous amounts of data. The 2017 data set is 5 petabytes, about a petabyte per station. How do you get that down? There are these lasercom techniques, free space laser communications, that do very fast downlinks. Avi, the answer is yes. Any kind of high Earth orbit station is interesting because it'll increase angular resolution. The picture I showed in Daniel's simulation is a low Earth orbit satellite that contributes less to increased angular resolution, but very much to time resolution because it's filling the UV plane so quickly. And I think we want to move in both directions. Sharper images through longer baselines, and better time resolution through the low Earth orbit idea, and they both have their challenges. By the way, the low Earth orbit satellite is particularly challenging for downlinking the bandwidth because it's orbiting all the time and doesn't stay in contact with a given ground station, would probably require a relay station in higher orbit, as would the far side of the moon, for example, although at submillimeter wavelengths you could countenance putting something on the near side of the moon as well. Have I thought through all the details? The answer is no, but without question, it's potentially interesting, yes.
All right, we need to move on to our next speaker, but let's thank Jonathan again. Thank you. Our next speaker is Dr. Maciek Vilgas from here at the BHI. Maciek is a postdoc working with the EHT, and among many other things, he's a critical member of the Calibration and Error Working Group. Today he's going to be telling us about the EHT dataset reduction and calibration.
Cannot see my presentation yet. Oh, okay. No, that's not my presentation. Okay. Hello, everyone. It's a great pleasure to talk to you about the EHT and about the part of the EHT project that I'm particularly fond of, which is data calibration. So this is the step where from the raw signals that are recorded at the telescopes, from those petabytes of raw data, we're getting down to a few kilobytes of the useful measurements that are used further for modeling and for the imaging. So this is quite a big challenge. The fact that it's a challenge is the reason why you didn't have those images a while ago. While the observations were taken in April 2017, we had to wait 2 years for the results. And a big part of that are the problems with the calibration. So I will briefly go through the main challenges of the dataset calibration. Well, first of all, there was actually no 1 millimeter VLBI image, no image constructed with that technique prior to EHT observations. So it's not like we could draw a lot of experience from well-established paths of processing the data. The atmosphere for 1 millimeter wavelength is very turbulent. You cannot trust the coherence of the atmosphere on a time scale of just few seconds. So we have to correct those effects on a time scale of just seconds. What you would do in longer wavelength VLBI, you would actually look at the calibrator and copy the phase from the calibrator. You cannot do that for 1 millimeter. There is not enough bright calibrators, and also this is a really quick variability in just few seconds. And also spatially, it does change. Well, because we are looking at very weak sources, we need to increase bandwidth to get more sensitivity. But because we increase the bandwidth, we actually cannot assume that properties of our detector are the same along the whole of the bandwidth. So we have to apply additional ways, additional corrections across the bandwidth. Our array is very inhomogeneous and it's very sparse. We have just few telescopes that are very different, so it's difficult to get preliminary image to which you could self-calibrate your data. There are a lot of problems relating to this inhomogeneity and sparseness. Two stations that are part of EHT are actually arrays themselves, so they need to be treated differently, and there are additional factors like phasing efficiency. How well do they interact as a single telescope, and how well can we assume that it's a single telescope? There are additional factors that we have to put in the calibration for those arrays. And also, the most sensitive part of the EHT array, the ALMA array, it's actually observing a different polarization component, component in different bases than all the other stations of the EHT. So there is additional step, quite complicated, that took a lot of time to debug, to provide right format of the data from our most sensitive array. Well, also when we started that in 2017, when we did record the data, we didn't have any mature pipeline. There was some EHT data previously in past years, but it never was that many telescopes, never that much of data. So all of that we had to, maybe not from scratch, but we didn't really have good software to start with. We had to code a lot of stuff up. So this technique that we used, very long baseline interferometry, the basic of it is the fact that we separate the telescopes geographically, that we record the raw optical field, turn it into electric signal, and we build the observation numerically at the correlator. The reason for that is a simple dimensional analysis, really. We need 20 microarc seconds resolution to image the thing we want to image. We can separate, if we want to, well, there are two factors that we have to consider. Lambda, wavelength, and dimension, the distance between the telescopes. So if we want to go to 1 millimeter, we cannot go any, it's difficult to go to even higher frequencies because of the turbulence. We are limited by this size of the baseline. This is about the size of the Earth, and this is what we mean when we say that the telescope of the EHT, this synthetic telescope, is of the size of the Earth. So this is interferometry. We are not recording the components of the image. We are sparsely sampling the Fourier plane of the image. So this is where we have measurements in the Fourier plane of the corresponding image. And this is the image, which tells you why we need those 20 microarc seconds. This circle here represents 20 microarc seconds. This is the image that we obtained. We cannot have much worse resolution than that. This is about the border of what we need to actually reliably image this data. So this is a roadmap, very short roadmap of how are we getting from petabytes of raw signal to the kilobytes of the data that is the stage of the analysis. So what we record is almost exclusively noise. We have to dig up from this noise the useful bit of signal. So these are petabytes of well, really, we are counting hard disk drives in cubic meters, and we are shipping those cubic meters of hard disk drives full of thermal noise from one remote location for many remote locations to centers of processing, to the so-called correlators. And that's the first step of the data reduction. So the correlation is really a moderately simple concept from the mathematical point of view. The big problem of that, the big challenge of that, is the volume of data that you need to process. So we have two streams of data recorded by two remote telescopes. We know the geometry, we know the locations of the stations, we know the position of the source in the sky. We have atomic clocks to tell us exactly what is the timestamp of the measurement. We put it all together to align the wavefronts to calculate the correlation between two data streams. So this is what correlator is doing, and then it does something that is familiar to everybody. I hope this is more or less Pearson-like correlation factor. So we correlate two streams of data and we average them down. And as we average them down, the noise has no purpose to be correlated between two remote stations. But the signal that we are looking at is indeed partially correlated. So this is what we are measuring. This is Pearson correlation, well corrected by some quantization efficiency factor. These are small numbers. This is not enough. We need to do more averaging, but we cannot because of the turbulence of the atmosphere. This stuff is done at two locations. MIT Haystack Observatory here in Massachusetts has their correlator, and another correlator is located in Bonn in Germany. And these are some of the brave people doing this data reduction, teams from Haystack and teams from Bonn. This is the part of the team from Haystack. And how much data is in this picture? The thing that Kazuo Akiyama is holding here, this is 8 terabyte disks, specially designed to be able to operate at this high elevation at the size that we are working with. This is a correlator, well, one shelf on the correlator, which is 4 times those modules of 64 terabytes. I would estimate that there is easily a petabyte of disk space in this image, plus a lot of, well, great capable brains, which I don't know what's the volume of this. Okay, so once we go reduce our data at the correlator stage, we are talking now about hundreds of gigabytes or low number of terabytes of data. So now this is something that we can put online and we can share. This is not something that would require us to move another cubic meter of disk drives to a different location. At this time, we are talking about data segmented in 0.4 second, and we are talking about complex statistical correlation coefficients, really. So it doesn't really have yet the physical unit to it. This is just the statistical correlation between two streams of data. In order to get anything more out of it, we need to average for longer than this 0.4 second. But to do it, we need to correct this fluctuation, this turbulence of the atmosphere. And this is something less automatic than the correlation. Correlation is more or less a mathematical operation when you set up things right. But this is something that requires to predict what is the fluctuation of the atmospheric phase and correct for that. So in order not to bias our results by doing particular choices of the algorithm to use, we developed 3 separate pipelines for doing this atmospheric phase correction, so-called fringe fitting. And 2 of them are more or less novel algorithms that were developed for the reason of this project. And one is the classic algorithm tuned up to be able to deal with these specifics of the EHT data. So this is the example how the phase is looking before and after this step. So you see these red curves. This is phase. Phase should be more or less constant on this time scale when we are talking about the phase related to the source signal. But all this wrapping that you see is really just turbulence of the atmosphere. And then once we apply our beautiful algorithm, we see that we really get to a particular value of phase. So all this atmospheric noise has been removed. And now we can average further because we don't get decoherence in our signal. We can average for many seconds now. And another trick that we are playing that is worth mentioning, we have few single dishes and this small array of SMA. And if you try to find a correlation between those 2 stations, in principle, you should get a nice detection. In principle, you should get, this is a function of time here along this curved line, and you should see what time delay corresponds to the best alignment of 2 data streams. This is just a function of correlation. Unfortunately, it sometimes looks really messy, and it's difficult to tell where is that detection, what time delay is required to be corrected for. Fortunately, we have this incredible array of ALMA, which is a very strong telescope. And the trick we are playing is we are using baselines to ALMA to constrain this fluctuation of the turbulence seen by this station and this station, and apply them together to correct for the detection at the baseline that is not connected to ALMA. And what you see here is actually real data. It's just arranged in a fancy way, but those signals are real signals, what you are getting before and after referring your face to this ALMA station. So this is one problem that we deal with. Another one is that another problem is that at this moment we only see the correlation between two data streams. We need to translate them to physical units of spectral flux density. So we need to apply some correction for the sensitivity of telescopes. This is just signal-to-noise ratio. And one thing that it's interesting to notice is that all the ALMA baselines are orders of magnitude stronger than all the other baselines. So you need to translate those coefficients to fluxes. So in order to do that, you need to make a separate measurement. And the separate measurement that we are doing is a measurement corresponding to sensitivity of each of the telescope or each of the stations involved. This is example of measured in kind of inverse of sensitivity. So you see how violently different is ALMA than all other our stations. This is really a very, very inhomogeneous array that we are dealing with. So now we will apply those corrections that you see here to our data. So this is our data, signal-to-noise ratio. We apply sensitivity correction, and that's what we're getting. So this is getting more and more similar to what previous speakers were showing you. But we have one more trick to play that Jonathan already hinted at. We have this network calibration additional assumption. The assumption is that because we have two stations that are collocated, in Chile and in Hawaii we have two stations, we can assume that the baselines to Chile and Hawaii on both redundant baselines should be seeing the same thing. It's a very safe assumption for the kind of baselines we are talking about. So you see we are adding this additional assumption, baking it into the data, and then we tighten up our calibration. And this is very nice plot that we saw for the first time actually a year ago at the last Black Hole Initiative conference. And then we were started to trying to interpret this data. Could it be a ring? So that was exactly a year ago. So when I saw that, after this preliminary calibration round, when I saw that, I immediately ran to Shep Doelman, our first speaker today, and this is Shep Doelman for the first time seeing the image of a ring. Sorry, it's not an image of a ring. It's visibility data strongly hinting at the ring, but not confirming the existence of the ring. So Shep was really curious about that. We started discussing that, and then it took a few more months to get things to the shape that we could proceed. But that's the first time we actually saw the calibration. So we are here. Right now we can average for longer time. We are talking now about not about just statistical correlation coefficients, but at this point we are finally talking about complex Fourier components of the image. So now we have this Fourier transform of the image, sparsely sampled, and now we can proceed to data analysis. Now we are really talking about hundreds of complex numbers, not about petabytes of data. Each image is really few hundreds of complex numbers. And of course we need to validate everything. We need to be certain that we are doing the right thing, that we are not baking in systematic errors. I will not attempt to describe how much effort this is and how much different tests are we doing. I will just show you a lot of histograms hinting at the fact that when you see normal distribution, usually it's good for your statistics. So that's very heuristic argument. You see normal distribution in dashed lines, and you see empirical distributions of different tests of data with red and with blue curves. So it's more or less good because we are not getting distributions violently disagreeing with the model that we are assuming. And the last scientific comment that I want to make, at this stage, looking at the data, we can see something really interesting. We have 4 days of measurements, and we see that 2 days are consistent with each other, and then there is 3 days without the observation, and then we have another pair of days. And we can look at certain data products And we can realize that, look, there are 2 days that are consistent, then there is nothing, and then there are 2 days that are consistent with one another, but not with 2 previous days. So what does it mean? It means that not only we have taken a big load of data from this interesting source, and we possibly see this ring-like structure there, but also we see that this structure is evolving at our very eyes. We see a huge data variation there. Something is structurally changing in the data. So, really last slide to tell you that we were not, well, we are actually working for all this time. It's not that this calibration was left untouched, and this is the reason why it took so long, that we did this iterative process of generating data, testing data, releasing engineering data to the collaboration, getting feedback from the collaboration. So these are all the moments when we received new correlated data product. We needed to do this supercomputing correlation 7 times to get things really right. These are all the moments when calibration working group was releasing data to the rest of the collaboration, asking for feedback. And the green are special meetings where a panel of experts was considering our presentations about the quality of data and stamping it ready to proceed. So that was an iterative process that involved a lot of expertise and a lot of people from the collaboration. And that is really my last slide, Dom. This is the group involved in the calibration. So the core team that was producing the data, and you see a lot of people here that also contributed at various different stages. And thank you very much. That is the last thing.
Questions for Maciek?
Do you have by now a value for the total value of the flux in useful units like ergs per square centimeter per second radiated into 4 pi stereo?
What's wrong with Jański as a unit?
I'm sorry.
Jański is a unit that translates to those
okay, for you,
CGS
all right,
units.
do you know the total number of Janskis emitted by the source?
Yes, but the compact flux is about 0.6 Jański.
I'm sorry, is...
The compact flux of this ring-like feature is 0.6 Jański, we believe.
I cannot hear.
0.6.
0.7?
0.6, sorry.
Thank you. That was the question.
Any other questions?
How well do you need to know the location of the sites for calibration? Like, you have to know them within a kilometer, a centimeter? Like, how tight are we talking?
So the data that is provided to us has incredible accuracy of millimeters, and we don't really know what is the reference point there if you're talking about millimeter location. However, initially you need to match those wavefronts better than 1 microsecond, really. And microarc second is like 200 meters of propagation of light, I would say. So I would say that we need order of meter accuracy. Yeah. Kilometers would kill us, probably. Yeah.
All right, last question.
It's a very striking time variability you showed. Can you comment on that?
It's great. So I'm sure there will be
comments. The physical origin.
I'm sure there will be comments from the imaging people who are actually trying to understand what does it mean for the image domain, for the source. It's very clear in visibility domain. It doesn't mean that it's very clear in the image domain. We see that something is changing violently in the structure, but for instance, if this is close to the node location, a very small change of the source geometry can actually imply a huge change in phase. So it doesn't mean that there is a violent change in how the source looks like, but there is a very strong indication that there is some structural change.
All right, let's thank Maciek again. Our last speaker for this session is going to be Dr. Andrew Schell. Andrew is a grad student here in the Harvard Physics Department, and he's a newly minted PhD after successfully defending just a few weeks ago. His work with the EHT is focused primarily on imaging algorithms and GRMHD simulations. Today he's going to be talking about the imaging procedures for the M87 2017 data.
Great. Thank you, Dom. Yeah, so now that we have the data that has gone down from petabytes to megabytes in this very intense calibration process, I'm going to describe a little bit of how we convert those data into images and all the tests that we did to reassure ourselves that this image that we produce in the end was as robust and conservative as possible. So, of course, this is fitting into a long history of imaging M87 with VLBI down to sub-parsec scales with the VLBA and GMVA. And we see this jet going down from the largest scales of the galaxy all the way down toward the core. And the EHT imaging is really right here at the very center of this jet. And this was a huge team effort. This is sort of the imaging working group as of last year when we were first imaging these data. I'm sure more people have joined since then. But one of the really great things about this effort is people have joined in from all over the world, including a strong contingent of people here at the BHI. And I just wanted to acknowledge that. And also, I stole many of their slides. So thank you. So yeah, the basic problem in interferometric imaging is that every 2 telescopes that we have gives us 1 Fourier component of our image. And so this is not very much to reconstruct an image. And we get a little bit of improvement from the Earth's rotation. So as the Earth rotates over 24 hours, it sweeps out these tracks in the Fourier plane. Every pair of telescopes sweeps out part of an ellipse that then accumulates measurements over the course of the night. This, of course, is a big problem for Sagittarius star, which is varying as the Earth is rotating. M87 is more stable, so we can reliably assume that the structure of M87 isn't going to change as the Earth is rotating. And so all these measurements can come from one image. But still, this is a small number of measurements with which to work to produce an image from. So the basic imaging problem, if we had perfect data on those sparse baselines, would be that what we're measuring is what we're sampling is the Fourier transform, but we're doing so on sparse baselines, and so the multiplication of the Fourier transform with the sparse baseline coverage in the Fourier domain translates to convolution with this very nasty beam in the image domain. And so if we were to just try to directly use a Fourier transform to get an image back, we would get something like this. From perfect visibilities with very minimal noise. And EHT obviously has thermal noise and then also a lot of calibration uncertainties, which make this problem even harder. So it's, if we had perfect coverage, we could just inverse Fourier transform the data. But because we have this sparse coverage and there are an infinite number of reconstructions which could potentially explain the sparse data that we measure, we have to use some sort of algorithmic process to reconstruct an image from the data that we observe. So I'm first going to describe a little bit about what the different classes of algorithms that we used were for the EHT. So the first is the standard in radio interferometry that's been used since the 1970s, the clean algorithm. So the idea of the clean algorithm is that we have an image that is, if we just inverse Fourier transform our sparse data, we have a dirty image, which is the convolution of the true image with a very messy, dirty beam. And so then we go through an iterative loop of trying to decompose this dirty image into point sources in which we convolve all these point sources with the dirty beam. We will recover the original dirty image. And so we iterate through this loop many times, try to collect this collection of point sources, and then blur those point sources with a Gaussian at the end of the day to get something of resolution that we trust. So this is the standard approach. It works very well and works on a huge variety of classes of problems in imaging, but it has an initial problem, which is that you have to calibrate these data somehow to even get this dirty image in the beginning. And so I'll talk about that in a little bit. So in the EHT, we have, as Maciek mentioned, a really big problem from phase error in the atmosphere. So the fundamental thing that we're observing is correlations between these incoming waves to our 2 telescopes. But atmospheric phase fluctuations and water vapor in the atmosphere are messing up the time arrival of these waves and doing so on very fast timescales. So we don't have access to the absolute phase on any given baseline. What we do have access to is if you sum a combination of these phases around a triangle, it can cancel out exactly the different contributions from local, I guess in this picture there are clouds, but turbulence above each of these sites, and you can get a robust observable called closure phase. And these closure phases actually, as Maciek mentioned, contain a lot of the structural information of the source. So we see in M87 that the visibility amplitudes are very stable from day to day, but the closure phases can evolve rapidly from the first 2 days of observations to the last 2 days of observations, potentially indicating, definitely indicating source evolution, but potentially on very small scales. Another issue that we have in the EHT is that our gain calibration, though the CNE working group puts in a huge amount of effort into getting to measuring the station sensitivities as accurately as possible, there's still uncertainties left over in what the calibrated gains of our sites are. So there's potentially a difference, a multiplicative factor of these 2 station gains for every measured visibility when compared to the true visibility. And this affects some sites worse than others, but we can also form special combinations of these amplitudes called closure amplitudes, which are invariant to these errors in gain, but then are harder to plug into the imaging algorithms. So in adapting clean to work with these limitations of our data, with the fact that we don't have calibrated phases and that our amplitudes can also be poorly calibrated, we need to introduce a new step called self-calibration, where you first have to have some initial guess for your calibration. You have to have some initial source that you then tune all the gains to match that source as best as possible in the data. Then you run through the clean loop, and then you get a final image at the end, and you calibrate the data again to that image and iteratively go through the whole algorithm multiple times to try to improve your calibration solution as you're improving your image. And so when we started this process, just because of the sparsity of the EHT and because of the severeness of the problems with calibration, we were, when comparing to longer wavelength observations, we were wondering if we could potentially try to investigate new classes of algorithms that could solve this problem in a different way to compare to clean and then increase the reliability of our results. And so the sort of natural approach that we settled on, which comes a lot from incorporation of Bayesian techniques into imaging and also from the computer vision community. Katie Bauman brought a lot of this thinking with her when she joined the EHT, is to instead approach the imaging problem as a forward model problem where you have some trial reconstruction, you forward model your system as best as possible, including all of these calibration uncertainties, and you get some likelihood for how likely your simulated data from your trial reconstruction is compared to the true image. And this likelihood can incorporate all of these different effects, like the systematic gain error and the atmospheric phase that we discussed. And then, of course, we can combine this likelihood with a prior, which in this case might tell us that these sort of very noise-like images on the diagonal here are less likely than sort of compact images that we might observe on the right. But then we, of course, want to make sure our prior isn't over-informing the choice of image. It turns out that in the imaging context, actually interpreting what we do is we don't actually use sort of a well-defined statistical prior, but we use what we call image regularizers, which define certain characteristics of the image that we want to enforce, such as like they aren't too spread out as these noise-like images, and we combine them with a log likelihood in what the formalism we call regularized maximum likelihood. And so this is basically just minimizing a sum of different data consistency terms with different regularizers, which enforce different characteristics of the image. In the absence of data telling us otherwise, we might expect the image to be sparse or smooth or to have other characteristics. So this is a really flexible framework that allows us to incorporate new ideas about how to approach the imaging. It allows us to work with the most robust data products directly. But it has a lot of new knobs in it, which are these new hyperparameters, which we have to tune the relative weight of these different strengths. So that was how to exactly tune these hyperparameters was a big question when we were first starting imaging M87. Can we robustly figure out a way to set these different weights? And these were developed in 2 different software libraries that really went in parallel over the course of the last couple years and have really strengthened each other by comparing to each other and then comparing to the traditional clean algorithms. So some of the regularizers that we use are things like sparsity, where we favor the image to be mostly empty space, smoothness, where we favor an image that might have smooth variation over spatial scales that might not be too sharp for the data, because of course we measure a maximum resolution, and we don't want to go too far beyond that. And then maximum entropy, which favors a compatibility with a specified prior image. So in this case, you might have an initial Gaussian that you'd want, we've measured a Gaussian size for M87 in the past, and we want our image in the absence of new data to resemble that. So we have these two different classes of imaging algorithms that we have applied to the problem of imaging M87. And so for the rest of the talk, I'll talk about how the process we went through for imaging M87 and how we verified what we were reconstructing is as trustworthy as possible. So the first step that we undertook was this blind imaging stage. So we got the data from the CNE working group about around the time of the BHI conference last year, and then we decided to break ourselves up into 4 different teams, sort of roughly distributed according to geography, and then image the data in total isolation for 7 weeks. And so we set this up so that we wouldn't allow ourselves to communicate, so that we wouldn't be influencing each other with the images that we came up with, and that we wouldn't, if one of us saw a ring and the other group wasn't able to get a ring, that the other group wouldn't be pushing themselves to come up with a certain structure because they had heard about what a different group was doing. And we really wanted independent expertise from across the entire collaboration, across the entire globe, to attack these problems with all the different methods that they could in different ways. And these 4 teams were also divided up sort of roughly into half and half using the regularized maximum likelihood techniques and half using the clean and self-calibration traditional techniques. Though several of the teams had experts who were familiar with both, and so could compare among the techniques within a given team. So we did this for 7 weeks, where we locked ourselves in rooms, and we prevented people from coming into the BHI and the other team, and it was all very difficult. But at the end of the day, we finally revealed our images to each other, and this was using a data set which is not the final calibration which was presented in the papers. So the data are different, and the imaging techniques were not as developed. So there's still some variation among the images. We didn't get exactly the same image for each group, but each group still recovered an image which has the same fundamental features as the image we finally published last month. That is, it has a ring of about 40 microarcseconds in diameter with an enhanced brightness asymmetry in the south. And so when we first saw these images, that was, I think, the first moment that we all, at least I personally, felt like this, was on its way toward being a real result, and that we had, this wasn't some trick that the imaging algorithms were playing on us. It wasn't something that I had coded into my particular algorithm to push toward a ring solution. Everyone had developed, had come up with this result independently. So this was us on that very first day. This is the average of all 4 of those initial images. And that was at the basement of the BHI in July of 2018. So our second step, once we had these 4 different images, these 4 different initial images from different teams, was to really combine our expertise, use the 3 different software packages that had been developed for the EHT, and to really try to attack the imaging problem in a systematic way. And in particular, to attack the problem of what are these different, how should we set these different knobs in the imaging process? So I mentioned the hyperparameters in regularized maximum likelihood that set how strong your regularizer or prior-like terms are compared to your data consistency terms. But then there are also lots of other different choices that typically an expert user will make as they go along the imaging process manually, such as what is the total flux of the source? And Maciek mentioned that the EHT shortest baselines are sensitive to a lot of flux from the extended jet that the longer baselines can't observe, so we have to make some choice about what the compact flux is. And then what are the initial sizes of initial models we might do? What level of systematic error tolerance should we allow based on the fact that we have all of these systematics that CNE did such a good job characterizing? So we attacked this problem by developing a set of different choices for 3 different methods, the clean self-calibration method, and then 2 different regularized maximum likelihood imaging software packages. And then we ran thousands and thousands of different combinations of these parameters over a grid search, basically, of tens of thousands of different parameter combinations. We tested each of these parameter combinations on a suite of synthetic data models. So basically the idea was, if we have these different synthetic data models, each of these models, actually, they look quite different visually, actually by eye, give you visibility amplitudes which are very consistent. So the M87 could have been this 2 point source model, and it would have still produced that bounce in roughly the same place that got us all so excited last year. And so these were the cases that we thought were the most concerning, that we wanted to really test. Could our imaging algorithms distinguish robustly between all of these different sorts of cases, all these different types of compact structure which could produce a ring? which could produce a ringing bounce in the visibility amplitudes, but are not a ring on the sky. And so we tested all of our different parameter set combinations on these 4 data sets, and basically the idea is we only selected the parameters which could distinguish between all of them and applied those to the M87 data, so that we were confident that if the M87 data were that we're using a set of parameters that's sufficiently general to image a lot of different structure and not just produce this ring that we had initially seen. And another advantage of this parameter search is that it gives us some sense of the, not exactly a distribution, but some sense of the variance and error that uncertainty we might have in our images depending on choices of parameters. We have a whole set of parameters that can well fit images, and we can start to look at what were the best choices. Some of the different regularizers, for example, the images are relatively invariant to choices of those. Some of them, like maximum entropy, it seems like it's really picking out a single value as the best choice. And we can also look at correlations with things like different characteristics of the ring across these sets of best parameters. So at the end of the day, we get, for each of these different surveys, one single fiducial image from our best performing parameter set for each 4 days of observation. So we have 12 images at the end of the day that are all images of M87 from these 3 different pipelines. And you can see that the fundamental features of the ring and the brightness asymmetry in the south are the same among all 12 images, indicating that it's stable across these methods and across time. The regularized maximum likelihood methods on the bottom 2 rows here are produce images with a higher resolution than diffmap, which has sort of this maximum resolution enforced by the fact that what diffmap is doing is producing a collection of point sources, and then it has to restore that with some beam. So we had a lot of debates about how we should combine all these 12 images, these best images that were selected out from each of the pipelines on each of the different days, into a single image. And what we settled on is to choose 3 images on a certain day, and then to blur them to equivalent resolution. So we put a lot of effort into verifying that we really think that we're getting additional resolution with the regularized maximum likelihood methods, but to be safe, we blurred them to the most conservative possible resolution, that of diffmap, and then combined them all into a single image. So really only emphasize the source structure that was common among all these algorithms, which again, in the broadest sense, is this brightness in the south and the overall ring shape. And over the course of 4 days, we can do the same procedure. And you can see that the structure is consistent over these 4 independent days of observations, but that there is some hint of potential night-to-night evolution, which we expect from the data. And you can see it's potentially showing up as a slight shift counterclockwise along the ring. Of course, we think the direction of the accretion flow here is clockwise, so this could be just some accident of some material lighting up in different ways. And one thing we're really interested in is going back to the data over the course of the next several years to really see if we can track this variability over longer terms. So I think I will wrap up there. Basically, I think in one of the later talks we'll talk a little bit about how we measure ring features from these images and how we can compare the ring features that we measure from images directly to model fits that we do directly to the visibility data, and how they're telling us all a very consistent story about the essential characteristics of this ring, and particularly the inferred mass of M87 that we get from this ring. So yeah, at the end of the day, the EHT used this whole community-wise expertise in VLBI imaging. We developed new methods. We relied on traditional methods, and we tested everything in many different ways, and eventually produced an image right here of the black hole at the core of the jet here at M87. So thank you.
Questions for Andrew?
So just to clarify, you first had the 4 teams working independently. Then you had the 3 images that you averaged to get the final image. Is there a connection between those 3 images and the 4 that the team independently?
I mean, there's a connection in the sense that we were all working on this whole process together. So the sort of techniques that developed into those 3 images that we averaged together many of them were pioneered in the first 4 images that we developed independently. But the second stage was really more about, as objectively as possible, choosing parameters for the 3 different software libraries that we had, as opposed to the 4 original teams that we had, which were more set up based on geography and as well as an imaging method.
So it was kind of like you took what you learned from the first step and then started again from square one and did it again.
Right, that's more or less it, yeah. But we were, now that we had all seen the initial image from the blind process, we were now comfortable working together on this process. Though, of course, different people had different expertises in the different softwares that we used.
Since we know the direction of the jet, have you looked into the prior of, is there any enhanced statistically significant signal in that direction? In other words, not having a flat prior, but...
Yeah. So I think we have looked at different sorts of priors that allow emission only along this direction, for example. And I think, unfortunately, at the end of the day, our dynamic range effectively is only about 10, or a little better than 10 maybe. And the jet emission that we expect from simulations is much lower than that. So I don't think we see anything that we think is the jet, and really we're going to rely on short baselines and filling in the UV coverage over the next few years, hopefully, to start to get better images of the ring, and then hopefully elucidate the connection of the ring with the jet, which we expect to also be there at 1.3 millimeters.
It's quite a vague question, but could you give us an idea of how the algorithms used in the blind imaging stage by team 1 to 4, how, qualitative differences between them, or different ideas or approaches in the algorithms?
Yeah. So we had the two different classes of algorithms, and so like I said, I think about roughly half and half. The teams 4 and 3 mostly relied on clean and self-calibration. I think they did this in different ways because they came from different experience and backgrounds in those communities. I can speak more to the regularized maximum likelihood method. Basically, team 1 focused on using software that had sort of grown out of maximum entropy regularization. So we focused on initial priors and initial source structure that we trusted from previous observations or from a relative size measurement. And team 2 really focused on these sparse imaging techniques that were really driving the image towards sparsity in the absence of data. But over the course of, so you can sort of see that in the initial images that the team 2 image is much more sparse and has fewer bright pixels. But over the course of the next stage, where we really brought the different methods together, we had a lot of cross-communication between these 2 software packages. And while they still don't do the same thing, at the end of the day, they're still relying on different underlying methods. In some sense, there was a lot of co-development that really pushed them to, I think, understand our uncertainties a lot better.
All right, so that's it for this session. Let's thank Andrew and all of our speakers again.